I would kindly request Professor Dr. Rajesh Malik sir to continue the session.
Thank you and warm welcome all of you here. Starting a kind of sharp show about science, about knowledge. Uh, I'm especially here because I wanted to. What I know is that there is a paramedic and this huge corpus actually challenging part of the of today volumes. Third, yeah, Michael, uh, certified trick.
You, sir, for your kind introduction. The background workshop, we are covering all aspects of system analysis and mainly trials. We are also the topics like that network analysis. Today's make us in statistics, but I thought that this there are a lot of interest now on the systematic and meta of the preclinical study. I will touch upon some of the developments which are happening. So before I start, I will have participants diverse backgrounds. So first question to the participant: how many of you have seen this photo? Yes, ma'am. Yes, this is Rajkumari Amritkar. But what does this photograph depict? Yes, 1947, Rajkumari Amritkar is receiving the penny from the first penicillin supply, which donated by Canada to India, 1940. And this is now that India became a manufacturer of Covaxin, and incidentally, it was exported to Canada also. His transition over 75 years underlines the importance of research, particularly in the preclinical phase, in case of drug development and vaccine. Now, Sir has, I had the chance to work during COVID time with Sir in very challenging situation. But COVID has taught us lot of lessons. And one of the, this is a very interesting, has been published by Professor Balaram Bhargav, the director of ICM. And I think it is worth reading this book of us. So this book you have read. Okay. So have you read the story of how yes. So yes, please, you stand up and say. Yes. So for those who are interested, you can watch this movie. This on the vaccine war. That actually shows what was challenging at the this has highlighted streamlining the research environment across all spectrum. Now, when I mean across all spectrum, what I wanted to say is the preclinical studies actually are or underemphasized in because India lacks that facility. At least before the COVID time, there. Now, what does this preclinical study goes? I'm not going into the detailed discussion of that, but we have a idea that this is any drug or any device or any biological agent. Before it is brought into, it has to pass through certain layers of screening. Animal study is one of that. And there are cell cultures, there are 3D organoids, there are animal studies, and so forth. Now, my job is to say, sensitize that how systematic review can play a role or whether there is any role that matter. This particular. Now, if you look at this, I think many of you may be familiar with this. So, this is actually showing the journey of any new device or any drug till it comes to the, and it has to cross through several proofs of principle. Now, here I have highlighted one area which is called the valley of death. 90% of the drugs or 90% of the agents do not see the light of the day, and that is because it fails in. Now, why that happens, what are the reasons of that? There are detailed discussion on the of today. But what we know that nobody can deny the importance of this kind of that change. Because if that change is weak, then the entire process becomes. And believe me, this is the weakest part in the research domain in India. Data shows. I will come to that in later. So, what are the benefits of systematic review in clinical study? Now, preclinical studies like cellular studies, like organoid studies, like animal studies, there is a need of evidence-based choice. Now, we always think that animal studies mean rodent studies, rat studies, mice. So we have a very generic idea about the choice of the animal, but many drugs actually fail. There are examples of that because of inappropriate choice. The classical example was in stroke. So they are very expensive drugs that passed through several layers of that did not show any benefit in the clinical trial, leading huge wastage of. So there are emerging scopes, and this is actually a concept of methodology. Now, what it is showing is that animal experiments often do not translate the replication of the result in human trials because biologically there is a there is emerging rule of. So now we are talking about utility not only at the level of histopath but also at the level of radiomics, is a very emerging field which is actually helping to characterize the heterogeneity. Not possible or so in uh, and there are, I think, currently almost than 180 parameters of kind of text, all which is now the right side actually shows the bioavailability of some of the drugs which are different from different species of. Now, this is one point. The next point is phrasing the research question based on human priority. Now, when we are designing an animal study, are we actually trying to uh, translate our primary objective to the animal model? This is a very interesting domain that has come. This is called the James Lind Alliance. The James Lind Alliance actually they are trying to identify the key research questions. For example, you have to develop a research also important for funding agencies. So, like for example, traumatic brachial plexus. Now, in this particular area, what are the human priorities? So it so happened that a detailed discussion where patient part of that. It identified some of the questions, and you can see here that psychological treatment improve this outcome came out to be one of the top priority for the patient. So this website priority areas of a research domain. So when you are designing a then you also have to the primary objective. Now this primary objective the human trial is not what is there in the animal study. The third question is translational transparency. So we are talking about translational research. Now, there are translation research, there are translation research. Now, how these translational transparency can be maintained in that chain of events that was search domain. Search. This is a very classic example of that. Some of you may. This is an Oxford trial of tuberculosis vaccine. So this was MBA 85A study. Passed through the animal trial. I think almost more than 3,000 ants were randomized South Africa, and then it showed that these. Then one group did a systematic review of all the animal trials which were quoted, the background, and then they found that there are gross animals. Actually, if a systematic review had been done for the clinical trial, this trial, I think Professor Pratap Therian would have shown you that slide, which is on the streptokinase. So, streptokinase randomized studies were done from 1959 to 1989. Almost 30,000, more than 30,000, I'm not remembering the number. This many patients were randomized into arms. One arm received, one arm did not receive. Now, one person did the system, all the trials, and then it was found that if the systematic review was done in 1975, then this further randomized trials beyond 1975 would not have been necessary, because that time itself evidence was there that so that highlights the importance of systematic review, and this is transparent. Then transparency in quality of reporting and reduce. We have all discussed in the past 4 days about this thing. So how to report human studies, how to report the human system. Same thing coming for the systematic review, animal trials. There are a lot of publications that are coming now. In fact, there are very good websites which will show what are the animal trials which are done on that particular such question. Some of these are shown here. Now, based on this, there is a Cochrane review also, like systematic review of preclinical animal study can make significant contribution to the health and more transparent trust. So that is a very important aspect now. And there are several available tools which are parallel to the studies, the animal details of that. There are websites which provides all those. Now I want to touch at the end points, 2 points. The first point, India is the leading exporter of the pharmaceutical. You can see this graph. So this graph is actually taken from the annual report of the Department of Pharmaceutical. And it shows that the current market of $10 poised to go to 120 for a period of 10 years. But the data from India, with nearly 1/5 of the global population, also achieving the status of leading exporter of the pharmaceuticals, the amount of clinical trial that is done is less than the world. It's actually from the clinicaltrials.gov. So this issue is very important, particularly in or for other medicine. So there needs to be a context-specific evidence which will deal with this condition. Now, if we analyze this information even further, so emerges that this actually shows the number of registered clinical trials in India, which is registered with the IC of different, and it shows dismally that the number of preclinical studies which are registered are very low compared to the phase studies. Not going the further analysis of this because it is sufficient to say that most of these are drug trials, most of these are multinational trials or sponsored trials. The investigator initiated the phase 1 trials, radiation trials, or diagnostic trials, those are very much lacking. The data from the now this also shows that this situation so we have not right such environment to develop the drugs. Number two, now we are moving main of system. We are looking at beyond animal study, beyond cellular. For 20,000 diseases, now the system biology has evolved from the level of the biological information, DNA, RNA, protein. So we have now genomics, have transcriptomics, have protein. And at each level, the information is, I think, fivefold or tenfold. The transcriptomics information 5 times, and so on and so forth. And now we are talking about some bench. That means what? That means we are trying to conceive digital twin. Now, what is this new concept? Horizontal integration of the different of the whole. So it is hypothetically or potential and sure prospect possible to design digital twin of an organism or for that matter a biological system, predict the process or which will predict the biomarker research or which will predict the outcome of it. Now this is what is going to be phenomenal change. You can say time shift. Now what is happening here? This is the paper 2020. The digital twin is not only going to change the landscape but for intervention, for diagnostic, intelligence, prediction, this prediction. And then there are so there, there are emerging platforms of digital twin that are already coming to the market. Now the research cannot over be prepared for this kind of cannot and the clinical trial concept changing. Now we have this in one model. That means that moment you have a digital twin, in a human trial, you can only one interview. But once you have a digital twin, you can give can give simultaneous n number of permutations. So this is the landscape. Now we are talking about R's. What are these three R's? Here's a reduction, reduction and refining of the animal. This is the purpose. This is possible by using, and it is also possible with beyond the animal studies because here you are actually simulating the human environment. The number of variables is the matter. The how many variables, but this is the future. So there are emerging the use of digital health early phase. So with this I will end, and this emerges actually highlights the challenges of the thematic behavioral study. How to take so much information. This most of the time this AI based learning systems are black box. That means we do not know how these informations are being processed. A very standard engineering to receive the signal, you give it to the system gives the output. In the traditional system, these systems are defined by precise math. But what is happening in machine learning or AI is that we do not have those parameters or quality assurance metrics. So some of these metrics are actually there, some of them are actually in search, but this is where the future system analysis. This I will next session and today for the whole day. Rightfully, we are having all statistics plus statistical aspect of systematic review and data analysis. And actually, I requested Madam to do the survival analysis because many of us are having difficulty analyzing the survival outcome in a systematic review. Particularly, some of the papers at trials are quoting mean survival, some are real survivals are giving confidence intervals, some are not giving confidence interval. So, Madam has agreed to in us how to do the time to event analysis. Thank you, sir.
Thank you, Saikat. And it's a privilege for me to invite Dr. Geeta Menon, who is scientist up in ICMR. He's a professor in the Faculty of Medical Research and heading the Division of Economic Assessment, Department of Research. Uh, I'm pleased, audience.
To all of you. First of all, I should sit together for many years of English. Actually, I was not a teacher before I joined the AIN department. The AIN department is technology department of DH. Sir, do you remember this? Yes, I had come for a meet. Now we are also a faculty of medical research recognized the SIR. I have the calling myself professor, although I haven't guided any student as such. So, good morning to all of you. What kind of audience is this? Are they all doctors and researchers? Do we have any? So, we are talking about statistics today. Hope you don't doze off the middle of the lecture. But it's an important topic, and for me also, it was first done a hands-on data analysis. So, it was for me also. Talking about time to event analysis, I will start off the basic concept of time to event, and then gradually on to how to track data as doctors said, how to extract the right kind of data for survival studies. So let's look at examples. The first example where this is trial that was conducted across 7 American hospitals on pairs of children who had acute leukemia, and they were initially treated with prednisone, and then later on they were followed up after administering 6 MP. 6 MP is 6. Forgive me for my pronunciation, doctor. Captopril, right? So they were given to these pairs of children, and then their time of remission was recorded. So each pairs and each their time to relapse or time to relapse in the placebo and time to relapse in the treatment group was recorded. So we look at this data and then we try to understand what. Second example is time to infection of kidney analysis. Patients who had kidney problem, they were treated. They were given dialysis, different catheterization procedures, the surgically placed catheter and the percutaneous placed catheter, and their times were recorded. As you see here, the infection times for some patients are there, and there is something called censored observation. What are censored observations? We learn. And these are the two groups of patients. The third example is on the time of death of patients with bone marrow transplants for Hodgkin's and non-Hodgkin's lymphoma. And you have the two types of NHL, I think, autologous and allogeneic. And the time for the two groups of death or relapse has been given here. If you look here, delta I in the middle one. If you see this, the delta I after I ordered as 1 or 0. 1 means death and 0 censored. So this one more example where time to cosmetic deterioration of breast cancer patients who have been treated regimen. One is radiotherapy alone and the other therapy and chemotherapy. So if you look at this data, there is a round bracket for some patients, square bracket after that. Or intervals. Start of the treatment because round exactly at what point right, they had the disease, and the square bracket actually the event observed. And for certain other cases, they are greater than or equal to 38, greater than or equal to 40, which means that the time of onset is not known. Have been time for cosmetic disease more than months. Have such data coming in from, and the other last example here is time to eat, where induction time has adults and action time is already mentioned here, and how to analyze things of analyzing such. Right? And you have many more examples where you have the time free of time to conception in a and for time to resolution comes the health condition. These are all time related events. We cannot use the data, the year happening, not happening, and also time from the beginning. So survival analysis or time to event analysis, or sometimes it is called a method of analysis that is used to analyze the survival experience of individuals who are administered a treatment, are followed up over a period of time, and then They are they are see whether they have attained those events or not. How many of them, by how many of them are censored or leave or follow up study. All that can be by the survival analysis technique. So we do this by one because we are looking at time. All know that time does not follow you statistics and it is normally if the data is not normally distributed, then we try the statistics by analyzing the data. Time or duration follows a skew cannot for we cannot use the analysis. The statistics transform them logarithm transform or a non-parametric. Sometimes what happens in studies, not all patients attain that even. Some of them are lost to follow-up, some of them leave the study, some of them die, some of them, if not death, if it is say, recovery. And these are time points, all patients that do the event that you are before, and it is a follow-up period. And therefore, it is such cases analysis. Also, we see that some of the patients are censored. Censored means they do not set it for some reason. So if such patient need to be their data is for us at their survival experience also. And sensory can be of two types. One sensory, one is left sensory, one is well sensory. So if a patient right sensory endpoint was has not reached at the time of observation, cannot continue a trial for years together because of resources. Have to stop the trial at some point of time. If at that point of time, the event that you are looking for, say for example, if it is death, if it has not been attained, then the patient continues to be, he assumed that he's been alive even after the time of the study is over. So such patients are called right censored. They haven't attained the event that we are looking for, or they are lost to follow up during the study period. Left censoring means we do not know the beginning point of the when he actually had the onset of disease, but we know the right point where has attained that event. That is called left sensory. Sometimes what happens is in a clinical trial, we do not have the left sensor, we don't have the time points when the patient enters the study, and we do not, we have the time points when the patient leaves the study, but we do not know something in in between, whether the patient has, oh, it's the other way around. So the interval censoring means you have the interval when the patient attains the event, but we do not know for the end point of study. Such cases we talk about the with sensory. So there are these are the different types of sensory in terms of time period. Other thing is that the effects that we usually use for meta-analysis. What are the effects usually we use for meta-analysis for comparative studies? It's either the odds ratio or the risk ratio. So odds ratio or risk ratio measure only the absolute number of events. So it is not time dependent. So what you can do is if you are observing a patient over a period of time, at each point of time you can calculate odds ratio. But then there is no method by which you can combine all this because different trials report the times of follow up in a different way. There is no way you can get the odds ratios together, combine them, and analyze the data in the usual manner. Therefore, all these reasons we have to actually conduct survival analysis. Now, this is a graph where we type of data that we require for doing an event to time to event analysis. First, the time of entry into the study is very important. The second is the time when the study ends, either the time when the study ends or either the time when the outcome has been reached. these two points are very important. Time points is very important. Should have the follow-up data of each patient. For doing a survival analysis, each individual patient data be available. This I'm talking about single study. I have not come to meta-analysis yet. And then the outcome status, whether the patient attains the event or he does not attain the event, or has he left the study. If you see the graph here, as we record it in a calendar time, because all patients cannot be entered into the study at the same point of time. So they over a period of time the patients enter the study, but then this calendar time has to be first converted into the time or duration kind of data. Then only an analysis can be done. How do we do it? If a patient starts, if you look at the first patient below, he entered the study in 1990. So the time of the study when the patient enters is a zeroth time for that patient. Okay. And then he is followed up over a period of time. So 8 years he is followed up. He is lost to follow up at the end of the study. So this patient is called as censored patient. He has not attained the event. The second patient, if you see from below, he also started slightly early, but somewhere around that time only. And the beginning of the study is mentioned as 0 years here, and he is followed up over a period of time. And if you say A is the he's again a loss to follow up because he attended the clinic at the 10th year after his induction into the study. After that, we do not know the status of this. So this is again a patient who has been lost to follow-up. There are other patients, for example, if you look at one of those studies where it's X at the end, those patients have started, we know the time when the patient enters the study and he has attained the event before the study ends. So such patients are also there in the list of patients, and they need to be incorporated. The time duration needs to be incorporated in the analysis. So the primary goals of survival analysis is one, to look at the survival data and evaluate its survival and hazard functions. What is hazard? We'll talk about it. And again, compare if there are more than groups or more than two groups, to compare the survival experience of patients in each group, which is very important, especially in cancer trials. And then also try to investigate the role of other variables in the survival function. So all this is and there are more, but these are the primary goals of survival analysis. And this paper, this is important because those who are new survival analysis, the terms that are used in survival analysis are all given in this paper, and one can go through it because these terms are very commonly used in survival analysis talks as well as in presentations. Necessary to understand the definition of each one of these terms. It's a good definition which all the terms. Now, survival analysis, survival probability. As I said, there are two types of. One is survival probability. Survival probability talks about the survival or probability of an individual who has survived one time period just below before the time that you are concerned. For example, you're talking about survival of 10 years, and survival probability says that the probability of an individual survives up to the ninth year and is the time period that you consider. And what the survival of that patient short period of time from the ninth year to the 10th year is a survival probability that one talks about. And statistically or empirically, the definition ordered like this, where STJ is a survival time at the jth point of time, and that is nothing but that the patient has survived up to the j minus 1th point of. And then what happens is that probability times the probability or the proportion of individuals who are remaining in between jth and minus 1th time divided by the total people who have been carried over till the jth period of time. These understand all this, but the concept that whatever we talk, statistics, we have to convert it into numbers. Then we can analyze. So that is what is the probability of survival in given time. And this is all based on the actual science that that is based on life table approach. We'll talk about it, and there are formulas you can go that that are used to calculate the number of individuals at a particular point of time, using the number of things that has happened during that period of time, and what is ultimately the survival probability at that point of time. This is based on actual science, and also the survival analysis that we talk about in all clinical trials, the Kaplan-Meier approach, right? Kaplan-Meier approach. And if you want to read more about this, this is a B&A publication that very detailed explanation of the whole process of calculation. The mathematical process by which we calculate the survival probability. Take some examples to understand whatever we have said. Say, for example, there is this example where two groups of patients who have received radiotherapy with or without adjuvant chemotherapy. 86 patients in the radiotherapy group and 78 patients in the other group. And these are the times recorded for each patient. So we have all the times for each patient. Remember, when we do survival analysis, we need to have the time data for each patient. And somewhere you see the A age there. Those are the ones who have been censored or lost to follow up. So these patients do not attain the event at that point of time, and they have been censored. And then this on the right hand side, each time point is considered for each of these patients, and the Kaplan-Meier survival functions are calculated by the methods that have been published in papers. And then after that, a survival function is drawn. So this survival function actually describes the survival experience of the two of patients. If you see, there are two curves here, and these two curves depict the survival experience of the of patients, one who have received radiotherapy and chemotherapy, and the other who have not. And if you see this curve, just randomly, can anybody tell me which improves the survival? Combination improve. That's because of your clinical experience. But otherwise, if you are a layman, can you make out from this graph? Yes, you can, right? Because it tells you the survival function, and especially if you look at those dotted lines there, that provides the median survival time. And if you see the median survival time of the radiotherapy alone group is 0.64 months, whereas the median survival time for chemo plus radio is 1.1 month, 1.1 years, I think. So, better survival of patients who are given both. So, it's a lot of information. The Kaplan-Meier curve is actually a method of depiction of the survival experience and also comparison of the two groups. Okay. So now, coming to the next point, how do we compare these functions numerically? There are methods of comparison. One is called the log rank test, also sometimes called the Kaplan-Meier method of comparison of two curves. And the log rank test is used to calculate the events that are observed. One is the events that are observed clinical trial. Then, in order to calculate log rank test, you also need to have the events that are expected, and that formula is already given in the book. And that together with the observed events and the expected events, the log rank test is where the two survival functions. We want to know, and if we just by really, if you just know that these two curves are significant, have to statistically, and you have to give that p value, the sacrosanct p value that we all depend on. And for that, we need this test for the log rank test. Another function, as I said, one and the other one is called the hazard function. What is a hazard function? Hazard function is actually the opposite of survival function. Probability that an event has happened in a short period of time. Person lives up to the jth time period, j and j plus one time period. The person attains an event or dies or whatever is the event. That is the probability that the hazard function talks about. Hazard function, the function that we are going for meta-analysis of survival study. So it's very important. And in terms of mathematics, we have alpha, beta, theta when you were 10th. So it talks about the limit that as the survival, the time period between the 30th and the plus 1th uh, time reduces as it tends to zero, it gives you the number of survival or the probability of survival. An instantaneous probability that is has not experienced an event that time period from 0 to t experience as an event in a short instantaneous time period. And then we also talk about hazard ratio in analysis. What is hazard ratio? Hazard rate over of the experimental group over the hazard rate. And this hazard ratio is the effect that we are analyzing the. And then hazard ratio has its own characteristics. It positive probability it varies from probability varies from 0 to 1. So the probability lies between 0 and 1. And if how do we interpret hazard ratio? Hazard ratio of 0.5 means that at any particular time, half of the patients in the group experience an event as control group. And if the hazard ratio is 1, if the odds ratio is 1, what happens? How do you? Hmm? Yes. So like the likelihood of experience in the two groups is the same. And as we interpret odds ratio, we can interpret hazard ratio also. We should also understand that hazard ratio being a ratio, it gives you the exact probability for a clinician to talk about when he is following up a patient. If it is also called it is helpful in calculating the odds or probability of obtaining an event. If you have the hazard ratio, you can convert it into the probability, and we can convey that message to anybody, communicate that information to anybody. We'll take some examples here. Before that, we said it's too much of statistics, but what I wanted to say was that hazard ratio has to follow a proportional hazards assumption. And what is a proportional hazard assumption? Under this assumption, proves that there is a constant relationship between the outcome and the covariate vector. So, in other words, if an individual has a risk of death at a particular point of time, the initial stage of the survival experience is twice the risk, continue the same manner during the entire time period. Proportionality does not change. This is the only way I can explain it to you. But this is one assumption that the hazard ratio has to follow. There are methods of testing the proportional hazard assumption. So when an analysis is done, we have to first heard about Cox proportional hazards model. And in the Cox proportional hazards model, the hazard ratio has to follow the assumptions for it conducted. Let's look at an example which is easier for you to understand. There is a randomized controlled trial to investigate the effectiveness of a new treatment for improving the survival of patients with heart failure. Treatment group has 125 patients and control group has 123 patients, and the primary outcome is overall survival rate. Okay. So after the results that have been given in the paper is this. After a median follow-up of 1500 days, the hazard ratio for death in the treatment group is 0.38. For a clinician, what does this mean? How do we interpret this data? What is a hazard ratio and how to interpret this information? How can I read these figures and what are the main findings of this paper? And how do we communicate this information to other person? So, what it says, the curves that you have seen on the right hand side, that tells you a lot of first information, as you have seen, that it gives the overall survival experience of groups. So as we see here, the treatment group is much better than the control. So the treatment group is blue in color and the control group is green in color. Also tells you in survival time. Also tells you those vertical small lines on the graph that gives the censored observation. Have not attained the event, the time interval of observation. Those patients are marked as censored observations here, and the time in days is mentioned on the x-axis. The patient's probability of survival of the patients on the y-axis. This curve gives a lot of information, and this information is extracted for conveying this to the group. Particular case hazard ratio is 38%. Means probability of death in the treatment group is better or worse. Tell me. Hazard ratio is the probability of treatment group over probability of occurrence in the control group. Now, hazard ratio of 0.3, which group is better? Treatment group is better. By how? What percentage? How much percentage is of death is reduced? 62. Very good. So 1 minus 0.28 tells you that gives you the probability that there is 52% less likely of death in the patients in the disease treatment group as compared to the control group. So treatment is definitely better than the control group. And the confidence intervals are also mentioned. With the confidence intervals, the percentage of survivors varies from hazard ratio varies from 0.28 to 0.53. How will the probabilities vary from 47 to say 7, 47 to 72? That is how you have to interpret that. It is given, but we know how to interpret.
Let's say, so, example, the y, then how to
Don't take survival as term survival. Survival does not actually mean survival. It means time to event. It can be negative event also. The probability of death, or death is a negative event. The probability of death will be on the y. Got it? So what I am trying to say is survival does not mean survival. A portion of death can also be there on the y.
y-axis
Meant for probability.
of death.
The recurrence go like this. Curve of recurrence is always like, or curve of recovery, I mean. Positive curve will always go like. So it goes on, the study goes on, but we are looking at a cutoff of 1500. The patients may survive after that also.
Suppose
Mhm.
or that ratio interpretation
So survival will be recurrence. Survival will be recurrence free. Hazard ratio will always have an opposite curve. We're talking about survival function. Survival hazard ratio curve will be in opposite. But hazard ratio is given in numbers here. Survival function.
Also, because there is we are giving now suppose it's time recurrent of day.
Hazard ratio time to recurrence is the recurrence is the event for
Recurrence is
recurrence
now
is the
then
event.
should I say intervention arm having I'm just trying to
No, no, no.
understand.
Hazard ratio here also is like that. That is also in recurrence is also a negative. So if the hazard ratio is 0.3, the hazard ratio is 0.38, it's the same. Non-recurrence, you're talking about non-recurrence, we're talking about a positive event, so 0.3, 1 minus 0.3. It always be interpreted like that. Hazard is always the event of. Okay. Another example where a patient has recurrent herpes genitalis and the researcher is interested to know how episodic treatment with a new antiviral drug will improve the signs and symptoms of the recurrences. So we have a survival curve here. We have hazard ratio of 1.9. Now, maybe this example will answer your talking about recurrences. We're talking about recurrences. There is an antiviral drug which actually has to improve the symptoms of recurrence. But here, if you look at the hazard ratio, it is 1.9. It is more than that. Huh. So it's not doing, not improving. That's what it means. Hazard ratio is 1.9 and the median, but here this hazard ratio is reported for the lower of the two drug doses. The lower drug is on the top and that is a comparator. The two doses, upper dose is the comparator probably, control group. Therefore, it is the lower one has a hazard ratio of 1.9. The lower drug is not effective, right? So, and the median survival time is uh, 33%, almost 2 days. That median survival time you can calculate by drawing a straight line from point 0.5 to 2 curves, and that gives you the exact time period.
But doing that is the two factors and higher. Right? That which one was
I think you mentioned this point.
that to
When you feed the data in SPSS, you have a control group and a treatment group. The lower will be, say for example, if you're looking at, if you're terming 0 as the control group, then lower will be written as 0 and the upper one is written as 1. Typically, it means that the reference group is the one with the smaller number. Okay, so very important question. So when you the data or when you get the data set for SPSS, please remember that the reference group have a smaller number and the comparator group or the treatment group will have a higher number. It can be 1, 2. Automatically, it is one line. The questions that a clinic can answer after reading the paper is one, does this drug really work? Yes, it works. Yes, a clinical study has shown that the new drug promotes, because the new drug is a higher drug, a higher dose. It promotes healing. What are the chances a patient will do better on this new drug compared to no treatment? The odds are roughly 2 is to 1 because the probability is 60%. How did they arrive at this probability? Formula of hazard ratio and probability. The researcher has calculated a probability of 7% that you will have an episode of shorter duration than someone who did not take the drug. Talking about a person who has not taken the drug, not even the lower drug. When will a patient heal if he uses new drug? The study showed that about half the people who used drug were healed within 4 days. How did you get this answer? By looking at the median survival time. 4 days and 95% 8%, 8 days. How much good this drug will do to a patient? The new drug reduced the healing time in the study compared to a placebo group did well. That's what the study shows. And drug treated patients had a median healing time of 4 days as compared to 5.9 days in the placebo group. Other group. Hazard ratio computed. Now we are slowly entering into that meta-analysis phase where hazard ratio can be computed by these formulas, and there is a log rank hazard ratio and the mental hazard ratio based upon the kind of data you extract from the formula and then combination formula also. So this is what it means. Then coming to meta-analysis of time to event, learning about meta-analysis, here you all know science interaction analysis. There are two methods of effect and random effects. There are two methods of analysis. The formula is the same for whatever effect that you that whether or the risk formula remains the same, only that effects change according to the study designs that we are putting in the meta-analysis. There include survival data here, talk about food hazard ratio, talk about odds ratio, talk about food hazard ratio, and the formula for simple formula, the log rank formula is given as the observed number of events minus of events divided by the variance of the log rank statistic. Formulas are all there. How do you calculate the variable text? And I can give you some references also. Formula calculate. Don't even have to do that in RevMan. You can the data extracted from us and get the. But the main question, as I said, these are software which you. But the problem is that extracting the data from every survival study gives you data in a different form, and we have to bring them all to the common format to have the data. So we will talk about the way situations where the data are reported and the ways you can reconvert them into formula so that you can use these software. And if straight away this confusion was earlier papers, nowadays the new paper they the earlier papers if you're combining the earlier papers they have random all formats. So we'll have to convert them, use that information anyway, isn't it? So we use that information and we convert this and we see how. But if hazard ratio and the variance of hazard ratio or the log hazard ratio and the variance of log hazard ratio or meta-analysis is given in these papers, it is just use that information, plug it into the formula and you get the results. And similarly, if it is a Cox proportional hazards paper, you can extract the beta coefficient table that is the of hazard. So that and the confidence is given that information. What happens is not so. Most of my presentation based on methods that have been proposed by Parmar et al. Here And this paper is also very full paper. And all my following slides are based the methods that they have proposed, where we talk about practical methods of incorporating data from studies. So the first situation is trial reports observed in the comparative trials, which is number of events group, number of events control group. So you have the observed events and you can calculate the expected events, and sometimes it gives the expected events also in both arms, and we can calculate hazard ratio of the observed data. This is the formula for calculating. The variance of the hazard ratio can be calculated first, and we'll see some examples. You common for trial reports the observed events in the experimental arm and log rank variance is given O minus E are given in the experimental arm and the control arm, and log rank variance is and hazard ratio can be calculated by this formula. We see one example. This I have taken straight from the Cochrane training slide, where because I should search for another paper. Paper talks about randomized trial of neoadjuvant chemotherapy in oropharyngeal carcinoma, where 5 in the paper itself has given the observed, the expected O minus E. Everything has been clearly given in case of O minus. This kind of data is available from the data. Straight away, you can use this to calculate the log hazard ratio and the variance and standard error of it. The data that is needed in RevMan for event to time to event studies. So this is a very clear cut case. You can use this information. Suppose a trial reports hazard ratio and the confidence interval. And the trial reports hazard ratio and the confidence interval does not give you the log hazard ratio potential. Log hazard ratio, or why we are using log hazard? Remember that hazard ratio is not a normal distance. Log transformation hazard ratio follows time to normal distance. Trying to normalize it. And so hazard ratio is given and the confidence intervals are given. Upper confidence interval, upper confidence interval, everything is given. Z score, everything. But we need to calculate the standard error of log hazard. There is a formula. So we use all that information paper and calculate standard log hazard. I'll give you an example here. An example where it's a published paper in which the author has given this information. The patients randomized in the experimental group and the patients randomized in the control group. The patient's number of events observed in the group, number of events observed in the control group. He is given the hazard ratio and he has also given the 95% confidence interval. And then log variance is not given, a hazard ratio confidence interval is not given, log hazard ratio confidence interval is not given, as a statistic not given, that value is not given, but the p value is given. Okay, and then so many other things, the follow up details are given. Minimum follow up is 4 months, maximum follow is 82 months. All this now using the previous formula, we can calculate log hazard ratio. Hazard ratio is also natural logarithm of hazard ratio. Calculator will do it, and you can get a log hazard ratio of minus 0.1. And also the variance of the log hazard are the previous formula, the confidence intervals, uh, and then calculate variance. From the variance, standard error is square root of that. And so this is one way of doing it, and you can use a mental Hansel formula to combine them, or you can use a log rank method. You can combine the getting because O minus O minus available. Can use formula calculate required in time. The fourth situation is when the trial reports hazard ratio and the events in it, and we know that it is a balanced randomized 1:1 ratio. So one patient goes into the arm and one in the experimental arm. When hazard ratio is reported, without a confidence interval, the number of events are given in each of these trials, and also we can calculate required information. The formula for calculating the variance, log rank variance, is observed events in the experimental group into observed events in the control group divided by 2. So he is reported on. So you can use this information and back calculate all that. Not as back calculation, because there is no standard reporting method. And then calculate O minus E and B log rank. And the next one is trial reports the hazard ratio and the total event. Doesn't even total events at all. Talks about only the total events. If that is so, again you can approximately, these are direct methods of calculation. You can approximate and get the variance of from this, and the formulas. I can leave the slides. They are very useful. Not my information, straight from the paper, but you have to understand. But there are all situations have been discussed. The trial presents the hazard ratio, the total events, and the numbers randomized. It doesn't give you the events. Doesn't give events in each group, but it only gives you the number of randomized patients in each of these. You can use that information to calculate the required prices. Right? The V is available minus E. Calculate all that. I have taken the examples from the picture that I have first few slides. The example from this, I have calculated. You can link all those calculations. The information only this information has been used to calculate all that. So this is one question. Then comes, so we talked about this. So all those numbers have been incorporated in that paper. This calculation and the required information. Trial reports the p-value and events in each arm. It doesn't give you the numbers with denominator. That is so you still get that information from this observed events in the experimental arm multiplied by observed events in the control arm divided by total observed. And then the p-value can be used to back calculate the z. All know if a p-value is 0.05, what will be the z score? 1.9. 1.9. So you can back calculate that score and get that information required. And this one situation where trial reports only p-value and the total event. Then also it is possible. It's always possible. So there is no way we can put that paper in have back calculate and get the report represents p-value, total events, and the number randomized in each arm. Again, the formula can be used. Just times what happens is that doesn't give you anything, it only gives you the plan. So nowadays what's happening is that Parmar et al. What they have done is that if it the plan where curves are curved, and there is a way you can there is software which graphs. So that software can actually look at the graph at granular level. Time interval can be at points which are not shown here. Those points, the survival points, those points can be identified using graphs. And then this graph data extract created that this the time interval is 6, right? 60 months from 0 to 60 months. what the authors have done is that at 0th time there were 491 patients and 5 patients control arm. When you by looking at the curve, they realized that there was no censored observation. That happens, events were happening. The 12th month, there was no event that being done. And at 12th month, there is a drop in the so that number of individuals alarm to 72 and control arm to the authors or the systematic reviewer has to the graph track from that graph and look at whether it is there, it is happening at that time. And this is a data extract first created. Once you track data from the, then you have to this data to create the kind of information that we need. So there are different steps involved in this. One is the of event free at the start of the current because the survival function comes as time. So you have to data set that it is, and you have to calculate the event free survival at the start of it for that matter. The event free at the start of the prior interval minus events happening in the prior interval minus censored observation prior interval. Example, event free at start of the prior interval of 12 to 15 months. If you look at the graph here, 12 to 15 months. How many patients were there in the beginning? There were 491 in the experimental group. And if you look at the graph, second column, it says percentage event free on the research or the experimental group at the 12th time point is 70. So how did you get that 382.98? 78% of 491 at the time interval of 12. So that information can calculate from this. Okay. So the researcher has to do a lot of groundwork before it can be for analysis. It's better that when we publish, we give the information in a proper format for other viewers to track information. So the number censored can also be calculated this way. These are the formulas, and I have given examples in this for methods to calculate it. Same example. Numbers at risk during the current interval after assessment of censoring. That is important for us to of the survival analysis to do the survival analysis. Formula is again calculated and number of events during a current interval is the events in the current interval is those who are at risk during the current interval multiplied by the difference in the event at start of the interval and the end of the interval divided by the event start of the. So this information say you step by step you generate those estimates that we require uh, and then ultimately we calculate the hazard ratio the V and the O minus then entered into the RevMan. That this is also possible and we come to that and sequence of analysis you can just and then finally at each time interval and when we talk about the group combine it for all time intervals then only survival function for the entire group. So then you combine the survival agents at each time in this formula and get the hazard ratio. Hazard ratio is available in log hazard ratio. Calculate that. And if the trial reports the Kaplan-Meier curve and the numbers at risk, so sometimes we see the curve and the number can use that information also. Calculate the ultimately all this is together. So how to do RevMan? Once you have the extracted information, put it into RevMan. Main problem in survival analysis, meta analysis, survival study, fraction of studies. So I have told you almost all the situations where data can be from individual. This is the point. Thank you.
No, madam, I think this is what we actually wanted to understand from you, and you have very nicely explained all the situations. And this, I think, will help those because this is the most challenging part in the meta analysis. Because otherwise,
Want to add one? Combine appropriate way of doing meta follow up time and although some people issues but it's most appropriate but
there are any questions we can actually. It looks so complicated, but it cannot be simpler than this. This is the simplest way to tell. Anybody has question? Any questions?
right whether specific one of these they don't fit all these
Questions? So I have one question, madam. Like it's a statistic. Like we are observing the same. Now, when a variable is not having a normal distribution, when we take the log of that, it becomes near normal. What is the physical
uh, has to fit what we do statistics transform the way and do analysis but when we have to anti log of that then interpret the way you want like you're looking at log hazard but log hazard rate does not but there is a of that you take the exponent of log hazard rate that is hazard rate and you can
think that is very important. So it is like you are transforming that data to another domain, but coming back again to that domain and interpret. Because if you interpret in the other domain, that probably will not be same.
that's research then see coefficient x log hazard rate have to take exponential of that get the hazard
That is one. Second thing is like when a survival curve is crossing. Yeah. So is that does that mean that cost proportional hazard model is not applicable? Or
IMP oh, possible that the survival that case cannot clearly say that the Cox report violate and apply Cox report. Time period is gone and there is a crop.
third question is what is the difference between a multivariate regression and a Cox proportional hazard model? Do we need to report both? Or because it is also possible to get the beta from the multivariate regression. So in that case, there is no point of doing the
for a period of time. And then we have to do software.
I think that is another important.
For a
And suppose there are 10 variables in the trial, and when you do a cost proportional hazard model, how do you exclude the variable? What is the best method of selecting the variable?
tell you twice or step up or step down, whichever one includes model. Whether the p value is a high increment improvement in the
Okay, madam. So if there are no other questions, then I think we can conclude this.
scenario.
Yeah, yeah.
Anything that it software
The name of the software which will convert the Kaplan-Meier to the data.
first.
Hmm.
Have software.
Graph reader or something.
That software.
Graph extractor or something is there.
Make a scan of it and then you upload it into that software. Top points. All points. There are software.
Once we were doing with the survival analysis with one glioblastoma paper for meta-analysis, we had the same issue. And that softwares are there online also, and you can download also. Where they convert the entire, it's basically optical character readers, which convert graph and map it on a grid.
And the time points will differ.
you. Um, Morning, everyone. Morning. So I think holidays. I was just in the morning. Holidays are here. First session was statistics. And then you have to listen to the next two sessions on statistics. I hope it was holiday. So I hope end of the session uh, we get to identify few issues that are around meta-analysis, and I would just gear down a bit. Okay, I just put the gears a little bit down, then and then see if we can the basic issues before we go into and SCAPA, risk of bias assessments and things like that. Just get down a bit and then confirm certain very fundamental issues and see if we are on the same page. And if we are, then we kind of like proceed from there. So, so this is the outline that I had. Uh, you have like 4 hours together, right? Two before lunch and then after lunch. So hopefully, what we do is we try and complete till here, meta-analysis and its steps by lunch. And after lunch, we're still here. We look at challenges, heterogeneity, and biases. Okay, so man. So for me, I haven't done many meta-analysis. I've done a couple of them. But what I understood quickly is that meta-analysis is almost similar to any research study that you would do as a primary researcher. Okay, so it's not quite different from an ordinary research study that you'd have done either as a student or as a postgraduate or as an advanced researcher, right? So it starts with a clear question. You need to have a primary research question. That's you would have had sessions on that. I think earlier in your workshop, how to design the research question. Then you have to have a strategy for data collection, right? You need to have how you're going to search studies, what are the terms, what's the algorithm for searching studies, how do you ensure that the search process is reliable and valid. Then you need to have a strategy for data extraction so that you collect relevant data, right? Then once you have done these three steps, then comes the analysis or the data analysis part, where you look at how do you calculate what's called as an effect size from the individual studies. And once you have the effect size, then you try to synthesize results from studies, which we call it as meta-analysis. And then we try to look at interpretation from the synthesis. Right? So this part, together, calculation of effect size and synthesis, the quantitative synthesis part, and then the qualitative interpretation to the results, what we term it as analysis. Okay. Um, so that I think that's the first principle. So when you're getting into meta-analysis, I'm not sure how many people would kind of follow up on doing a meta-analysis. But if you're planning to do a meta-analysis, I think it's good to keep that in mind, right? It's not very different from doing a primary research study. All the principles that you learn doing a primary research study comes in quite handy. The first part is about types of outcome. Very important to know what type of outcome data that you have. We're going to talk about two types of outcome because Ma'am has told about the other important one. First type is called as dichotomous outcome type, which means you have the outcome variable that can take one of the two values. Right? So it can exist in only two states. Either it's present or absent. Either it is an yes as a response or it's a no as a response. So if you have a variable
I can have one of the two possibilities at a given, you would call that as a dichotomous variable, right? And that's the variable that is quite familiar to all of us because it's just simple and easy to understand. You have one or the other as two possibilities. And if you want to add to that, you can say that that kind of a variable comes from a classification process. If I come here and then I look at, okay, there are males and there are females, right? And then I can say, okay, there are people who have understood, people who have not understood. So if I do have this classification process, then the resulting data is going to be dichotomous. Okay? So when you see a dichotomous data, the underlying mechanism that generates the dichotomous data is a classification. Next one, called as the continuous outcome variable. So here, the outcome can take any value within its range. So if you have an outcome variable, and if I say it's a continuous outcome variable, then it means that a particular variable can take any value within its range. So you assume that there is a range for a given variable, and if that variable can take any value within its range, so if I put a finger somewhere, and if that value is possible, then you would call it as a continuous. Okay, so anywhere on the scale, if I put my finger on, and you say that value is plausible value for that variable, and we call that as a yes, right? And you can understand as well. See, we say continuous because there is no end to the position. I can say 150.5. And someone, if you have a good measurement instrument, you can say it's 150.51. If someone else have a very good measurement instrument, can say it's 150.512, right? There is no end to how precise you can be with a continuous measurement. Exists a continuous scale. And as I was saying that, you might understand that it depends on a measuring instrument. Right? If you don't have a measuring instrument, then you won't be able to produce or generate a continuous variable. Right? So if you don't have an instrument, if you don't have a measuring instrument, then unlikely to have a continuous variable. So if you have a continuous variable, you presume that there is an instrument which you use to measure that continuous variable. Right? So that's the first part. Two primary types of outcome variables. One, we call it as dichotomous or binary outcome variables. The other one, we call it as continuous outcome variable. Now we have these two outcome variables and you have an individual study. Right? So if you're a researcher, you have done the study A and you have collected this outcome data. This outcome data could be one of the two, right? It could be either a continuous variable or it could be a dichotomous variable. You collected this, now you have to summarize this. Now you have to summarize and come up with what we call it as an effect measure. So what this effect measure stands for is the way that could represent or summarize individual study results. Right? In this case, if you have two arms, the effect measure, and if one arm gets the intervention, the other arm doesn't get the intervention, effect measure would quantify the effect of the intervention. Right? So using the outcome data that we have, we try to calculate an effect measure that can quantify the effect of the intervention. So that's the first idea. It took a long time for us to come to this effect measure because earlier we did not have an effect measure other than a p-value. Look at earlier meta-analysis. Meta-analysis before some time. Okay, we didn't have a quantity called used p-value as an effect measure. If the p-value is less than 0.05, consider that there is a strong evidence for the intervention, okay, which we still tend to think. So we are going to first talk about what are the different effect measures and how do you calculate and how do we kind of interpret them? So at the first level, you have individual patients, try to summarize and bring them to summary statistics call. Now you have, just like how you have done, there are people who have looked at the same question, produce study B, study C, and study, right? Each one of them have collected their own outcome data and they all summarized their own effect measure, correct? From the individual studies. So that's what you would do if you are a researcher. But if you try to look at it from overall, if you try to look at it from a reviewer, if you're a meta-analyst or if you're a systematic reviewer, you're trying to see how you can combine these effect measures together and come up with a, just like how if you're a researcher, you're trying to see how you can combine the outcome data, come up with an effect. Right? If you're an individual researcher, if you're a PI for a project, you're interested in how I can combine this effect data and then say whether the intervention works or not. Right? The same principle applies for a review. Trying to see how I can combine these effect measures together, come up with a pooled. Okay, so then that process is called as uh, synthesis or a meta-analysis. That's what we call it as I was just saying. And we try to synthesize those results, cross those studies, come up with an overall. When I say meta-analysis, what we mean is process of synthesization of effect measures. We're trying to synthesize the effect measures that were calculated in the first step, come up with pooled or combined effect estimate. Okay, that's what meta-analysis. But before we go further, I recently, sometime before, I read an interesting article about coffee and tea. Fortunately, in the break, there is no coffee option. Tea. Did any one of you have coffee this morning? That's so. So some people prefer tea, some people prefer coffee. But there's this article actually talks about what's the healthiest drink. So if you look at from health point of view, which one is more healthier, coffee or tea? What do you think? Coffee? It depends. I would I would suggest if you have some time there, you can read this article in Washington Post about this discussion. It's actually a review. It's quoted many research studies. Some actually say tea is really healthy, and they link it with many biological parameters. Reduces this, it increases this, makes you calm, relaxed. Some actually talk about coffee, and some studies actually say coffee is better. Okay, and then he kind of weighs both uh, coffee in one hand and tea in other, tries to come qualitative synthesis of. I was going through this, and then uh, as I was going through that, I also found a very interesting article published in Nature. I thought, okay, maybe it's not just in the popular uh, magazines or journals. There's also an interesting discussion within the scientific community, right? So it's in Nature. It's discussing about how tea can change someone's mood. Uh, and then they quoted many studies within that view, how, and they also provided a mechanism how it can actually influence someone's. So I thought maybe we can take that as an example, then see how some of these things, statistical effect measures, can be applied. So if it's a dichotomous data, I'm sure you're familiar with this 2 by 2 table, right? So you have this is a P101 kind of thing, right? You have the 2 by 2 table where the outcomes are here. I took calm from here in terms of like whether a person is calm, not calm. We see whether a person is had tea for his cup of coffee. Okay? And then we have these four cross-classified numbers within the table, standard 2x2 table. Okay, so if you're going to read this table, you'd say, okay, there are totally 132 subjects, right? There are totally 132 participants. Out of the 132 participants, you have 68 who had tea, and then you had 64 who had coffee. That's the number of people who got the intervention or who got some other intervention. And then you look at out of the 68, that means I'm looking at the first row. I'm saying out of the 68, how many had the outcome? In this case, the outcome is 17. 17 of them had the event of interest. And likewise, I can look at the second row. Yeah, out of those who took coffee, how many of them had the event of interest? Out of 64 who had coffee, 9 of them. This is the data that I have from one single study. Now I have a question of to summarize this data, whether tea has an effect on. Okay, how would I summarize? How would I look at this data, then answer this question about tea? Does it have any effect on event of interest? How would you do it? Don't know odds ratio. I haven't told you about odds ratio. Right? How would you do it? Just looking at 2 by 2 table. Proportions. Okay, which proportion would you look at? Okay, so one thing we could do, as many of you mentioned, is take the ratio of the proportions. In other words, we call it as risk. Right? We'll take the proportion of people who are calm in the T group and compare that in some way with the proportion of people who are calm in the coffee group. Right? To do that, that's called as a risk rate. So I first calculated the risk of being calm. You take T. So totally you have 68 people, out of which 17 were calm. So the risk of being calm is about 25%. If you took T. So we calculated risk by taking the number of events by the total number of participants in that, right? To do the same thing for the coffee group. Number of people who took coffee, 64, out of which the number of people who are calm is 9. So 9 out of 4. And that risk is about 14%. Okay? So you have these two risks. You take a ratio of these two risks, ratio of one over the other, you get what's called as a risk ratio. Risk ratio is about 1.79. Okay? So when you get a relative risk, you need to understand it comes from ratio of two risks. One is the risk in the intervention arm, and then the other one is the risk in the control or the placebo or in the comparator arm. So when you take a ratio of these two risks, call that as, now it is 1.79. In this case, what does it mean? Does drinking tea, you think it increases, reduces? Okay. So tea increases the chance outcome, which we taken it as. Now we go from risk ratio to odds ratio. You remember in the last one, I made it a couple of times that when you're calculating risk, taking the number of events and then you're dividing it by the total. That's how we calculated risk. You do odds. you don't divide it by the total. Okay? You do odds divide by non-events. The number of people who had the event over the number of people who did not have the event. Okay? So it's like say 1:4. Number of people who had versus the number of people who did not have. Called as an odds ratio. Okay? So if you take odds of being calm, very different from calculating risk. We're not looking at the denominator. We are saying people who had the event versus the people who did not. That is the odds of it. So you say odds of being calm when you take T is about 0.33. What does it mean? When you say odds is 0.33, what it could be? So if you say the chance of being calm is 0.33, then how is it different from risk? Okay? So keep this in mind. Okay, when you're trying to interpret what goes through in your mind, just keep that at the back of it. Okay? Odds of being calm for those who take tea is about 0.33. Now, what will be the odds in the tea group? So for the coffee group, 9 had the event, 55 of them did not have the event. The ratio of those two things is the odds for the coffee group. Okay? The odds for the coffee group is about 0.16. Now you have these two odds, just like what you did with the risk or proportion ratio of those two. Now the odds ratio for 2.26. The odds ratio for being calm if you take tea in comparison to coffee. How do you go about interpreting this? Okay, so you're saying the first option, so definitely the middle option is out. There is different class. So it's either the first option or the last option. What about the last option? Should I be wrong if I say the odds is increased by 6% drinkers compared to coffee drinkers? Would I be wrong? Okay, so this is another way in which you can express the effect measure in, in an easier language is to take the odds ratio, subtract it from 1, and then you multiply by 100 to get it to a percentage. If you take an odds ratio of 2.06, subtract it from 1, then you got 1.06, you multiply by 100, some percentage increase. Yeah. Okay. Now we go into the third measure, simplest of all. You already have calculated the risk first group. You already have calculated the risk in the second group. Earlier, when you're doing risk ratio, took a ratio of one over the other, divided one on the other. Now, when you do risk difference, arithmetic subtraction. So you say risk first group is 0.25, the risk in the second group is 0.14. So you subtract one from the other. Difference in risk about 0.11. Right? You can again ask this question: what does this difference of 0.11 mean? If it is no, does it mean no difference? If it's no difference, what would be the case? 1, 0, right? So if it is no difference, you're subtracting one from the other, so the risk difference is 0. Then since it's positive, so it means the risk in the first group has to be higher than the risk of being calm is about 10% more as compared to. Okay, so risk difference is easy to interpret, but then the so many different ways people can actually put it. So if you look at the first one, call as an absolute is what I showed you. Risk in the first group is 25, risk in the group is 14. You subtract one from the other, the absolute effect of drinking tea is about 11% in the chance of being calm. That's all. But what people sometimes do is they interpret it this way. There's a baseline risk is 14%. And when I say there's a 50% chance, 50% increase, okay? So they add the 14% to the 50%, and then they say it becomes 64. Okay? So when you say there's a 50% increase, in absolute term, this is what it means. Your baseline risk is about 14%. And when you say there's a 50% increase, 14% goes to 64%. Is that possible? Right? Because it's such a big effect, no? For it to move to 64%, you need to have 50% effect for the intervention. Only then the baseline risk of 14% can get to 64. So this 50%, what they actually mean most often when you read the relative effect. Okay? So what's the relative effect? You take 14% absolute baseline risk, 50% of the baseline risk. So 50% of the baseline risk is about 7%. Change the intervention does only about 21%. Okay? So a very common way people kind of go from one to the other, from absolute to understand when there is an effect measure, especially if there is difference, whether do they mean what they actually say. If it's a relative effect, has it been reported as a relative? Or if it's an absolute effect, has it been reported as an okay? It also comes in when you do sample size calculation. People come and say the intervention has about 50%, right? Which one of the two effects? Are we talking about a baseline risk going up by 40%? Yes, it's a absolute effect. 40% effect is a relative effect. Baseline risk does not go by 40%. It goes by 40% of the baseline risk, in which case it may not be that high. Okay? So you need to distinguish between those two effects if data is actually dichotomous. The third one is in terms of natural frequencies. So you say when you say 14%, it means 14 per 100. And when you say difference is 11, you are going to add 11 more people to that outcome. Right? So initially there are 14 people who were harmed. With the intervention, you're going to increase that 14 people or 14 persons to 25. Right? So the additional number of people who will be benefited by the intervention is about 11. So totally you have 25 per 100 as your number of people. Okay? Those are the three ways in which you can have a spin on. So we calculated all the three measures. So we calculated risk ratio. We took ratio of those two risks. We found out it was 1.79. We also calculated odds ratio. Calculated odds first, and then we took odds of those two, about 2.06. Then we find out the risk difference, about 11%. What about, so you have one 2 by 2 table, have three measures. You can use odds ratio, you can use relative risk, or you can use this. So how do you choose one over the other? So generally what have some parameters to go about it. One is understanding. By now you would agree with me, odds ratio is something which is hard to figure out, right? I asked you to interpret, you kind of had problem in terms of saying what that odds of 0.33 or whatever number mean. Odds is not something easy to understand. But on the other hand, risk ratio and risk difference is hard. So when I say risk ratio of some value or when I say a risk difference, much more easier to understand those two. So in terms of understanding risk ratio, odds ratio, risk difference gets point. Second one is consistency. How consistent is the effect measure for different settings? So if I have different settings, baseline risk differs cross setting. In this setting, the baseline risk is low, but in this setting, the baseline risk is high. Okay? Do I get same values across these? I should. So if you look at relative risk and odds ratio, they provide measures are consistent cross setting. Okay? But on the other hand, this difference varies baseline. When it comes to consistency, this difference is not a good measure because it varies with baseline. So when it comes to consistency, choose either risk or odds ratio. Okay, so initially we had taken out odds ratio because it was hard to understand. We brought in odds ratio. Now the third thing is about mathematical property. Okay, because you're not just going to calculate these measures, you have to use these measures further, right? It's not just you're going to calculate odds ratio as relative risk. You have to use these measures further, isn't it? You have to do something with it for the meta-analysis. You have to do something with it for further calculations. So we look for some mathematical properties. One of the mathematical, couple of them is one bounded nature of odds ratio. The other one is you can switch. So you can switch from event to non-event as your outcome, or non-event to event as your outcome. And you can do that and then take a reciprocal of the odds ratio, you'll get the same value. The odds ratio has a very interesting property where you can switch the event from one to the other. So that is one of the reasons why in many meta-analysis use odds ratio as a summary measure of effect. All right, so I told about dichotomous measures. Now we move on to continuous measures. The dichotomous outcomes. We said there are three effect measures: risk, odds, and risk. Going to continuous measure. As I said, it's going to be a continuous value. So you have a distribution for, let's say, one group, treatment group. You also have a distribution for another group, control group. Right? The distribution is summarized by the center, tells you the mean of the distribution. You can look at the difference between the as an effect measure. Okay? So this is the value that comes from one group, distributed this way. Have values coming from the other group, that is distributed that way. And then you look at the difference in the mix. That stands for difference in. So in our example, let's say instead of just classifying people as calm and not calm, after you come out with your question, ask you 10 questions, right? Based on the response from your questions, get a score, each one of you, right? And then I take an average of this score. Those who had coffee, the average score is about 20. Those who had tea, the average score is about 30. When you have average, we also need to calculate standard deviation. How much is the variance? Then we found out those who had tea on average had a score 13 point higher. Right? The score for those who took tea was 13 points higher as compared to those who took coffee. What do you say about that? Third one, let's take out the first one because drinking tea does not affect calm scores. Right? It doesn't affect what you expect, zero. right? The reference point would be 0, not have any effect. If it decreases, then it has to be negative. That's all you think. And if it increases, it has to be positive. Saying it's positive, so it has to increase the that all of us are in. Do you have anybody that's little doubt about it? No doubts. Huh? Actually, I think higher scores of calmness, score higher in my questionnaire, you are more calmer. Interpretation of the could be the other way. The higher you score, would be doing that case, he would be bad because your the scores are much higher as compared. What else? That's the first part. Second part is this 13%, 13-point difference. Is it really big? Which means tea and coffee doesn't make any difference. It's not big. Both are 0. Right? So it depends on the scale of the score, right? If my score is about 500 points, maximum you can score is 500. If I see a 13-point difference, doesn't mean much. On the other hand, if I see a score is only about 30 points, score 30, that's case your score is about 13 points higher, and it's really a huge difference. Okay? So the scaling of the score also makes a big difference. See whether it is in interpreting the result. First case, you don't know whether it's increased or decreased. The second case, you don't know whether it's actually doing any change in both directions. So we need more information. So we need information in terms of how we interpret what's the range of the scale or the scale of the. So that is to what's called as a standardized mean difference. Okay, because there is this interpretation problem is range of the scale, we try to standardize mean difference. So what we mean by standardization is take the difference that we found earlier and we need to divide by some index. Bring that difference in that index value. Suppose if you have something, any particular concept, but you have different ways of measuring it. So I said, thinking of calmness, I would have one way of measuring, and you would have a way of measuring calmness. Someone else would probably take a sample and then that sample and measure calmness. Okay, so there are different ways of measuring calmness or any concepts. And how do you bring all this together? Standardize. When you standardized mean difference. So the unit that we try to standardize is to the standard deviation. We take the mean difference and the index that we use is the standard deviation. So when you divide by standard deviation, you convert the unit in the units of standard deviation. Right? Earlier the mean difference was 13. If I divide that 13 by standard deviation, I convert that 13 in the units of standard deviation. Now I can say 13 unit difference not in the calm scores, 13 unit or whatever value I get in the units of standard deviation. I would say 0.5 standard deviation difference, or I would say 1 standard deviation difference. Right? So the difference between two groups is about 1 standard deviation or 1.5 standard. So I would do it for my study, which used a particular way of measuring calmness. He would use the same process, the way in which he measured the outcome. But when you bring all that, all of that are in the one single unit of analysis. So now we brought different things measured in different ways, one common unit called the unit of. To that, that's called as a standardized. do we use standardized mean difference? Can I use it for the first case? First case, second use, third, third is not. Is it? All of you agree? Third, you can't use it. And someone say why we can't use for third? Different units. Units are different concepts, right? So one is measuring pain, the other one is actually measuring a different concept, functional pain. When you have measuring instruments that are measuring different things, you can combine your standardized with it. Okay, so it has to measure the same thing. What about first one? Why do you say not? It has different, like a right? You're measuring quality of life. Some of them use a set of questions. Some of them seems set of questions. Idea is to capture quality of life concept. Sounds okay. What about second? Different units. Definitely you can't use for the second one. Some of them are not so independent. It's actually a related measure to body mass index, right? Then you can't use standardized standardization process. Okay, you shouldn't because you are measuring pain, and some of the scales are measuring. Thirteen, take the mean difference, and you divide by the standard deviation. Okay, so now we finished two basic steps, right? First, we knew what's an outcome data. We also knew how to summarize the outcome data. So we look at the outcome data. If it is dichotomous, have three measures. Use risk, odds, risk. The continuous data, if it's measured consistently, use mean difference. I think people have done different ways to use standardized. Okay, so that's the first second thing that mind when you're doing synthesis, when you do analysis. You have to think about standardization. Different people have done differently. How do you pool all of them in a way that it reflects the, the consistent? Right? Once you have done that, once you have calculated effect measures, then you go into the analysis of the effect measure. Right? You first calculated the effect measures for the individual studies. Now you're going to the analysis of the effect measures. That's what we call it as analysis. So it's a statistical method combining the results of more than one study, find an average or a common effect for an outcome across those studies. Okay? So I want you to go as much as possible about this definition. Sometime during this, I'll ask you which part of the definition kind of. So it's a statistical method. Want to combine the results of the more than one study. Right? You just need to have one more study. Right? Then you can do meta-analysis basically. Find an average or a common effect, neither for an outcome across. Okay. I also put in it's an optional part of systematic review. Means you could do systematic review and you don't need to do meta-analysis. There's no the thing has to whenever you do a systematic review, you have to do a meta-analysis. Okay? So then why do you actually do meta-analysis? The first thing is you want to have a numerical summary. You want to have a number quantifies the effect of want to quantify the effect of intervention. You may choose to do a meta. The second one is to actually increase the statistical power and precision. So this is an often quoted reason why you do meta-analysis, because individual studies will have small sample size. Right? You may choose to do only 30, someone may choose to do only 50. But when you pull all the things together, then what happens? You increase the sample size. You increase the sample size. Where does the effect shows? Effect shows in reduction of errors, like you reduce beta error, or the power gets increased. Okay, so because you increase the power, you have more chance of detecting the intervention effect. Sample size increases when you pool studies. As you increase the sample size, your beta error reduces. Beta error reduces, the power increases. Power increases, you have a higher chance of detecting an effect if it is. That's one. Second aspect is you also increase the precision of estimate. More importantly, not only you detect the intervention effect if it's present, you are able to say the effect of the intervention more precisely. Okay? You come up with a confidence interval size than what you could do with your individual study. That's the second reason why you may choose to do meta-analysis. The individual studies are wide confidence intervals. You want to get a precise estimate of the intervention effect, so you want to do meta-analysis. Third one is what I like the most, because you do meta-analysis, you have a point estimate. You could also explore difference between. So you can wonder, or you can ask, why is the effect different in different? What are the possible reasons? Right. So you have an effect size which you calculated. Not all studies seem to have the same. Right? They're all asking the same question. That's how you refine your question. Is the selection process. So you are comparing apples with apples and oranges with oranges. Even after that, there is a variation in the what could possibly be difference between the studies. In a way that you cannot. If you do a simple individual studies, you will not be able to explore that part. Right? Do you agree with me? Those are some of the reasons why you would. Comes other question is when you can do analysis. First question is, do you have enough number of studies? In my previous definition, you would need to have one more study and do analysis. Right? So what do I mean when I say you have enough number of studies? Put up analysis. Do we have to worry about sample size? No. Yes. Keep that in the back of mind. Okay, we'll come to this. Whether we have to worry about sample size. Then the second question is what just now I said in terms of comparing apples with apples and oranges with oranges. You need to ensure that studies are comparable. You may have a set of studies. Are those studies comparable? In terms of whether the participant characteristics are similar, more or less. Are the settings similar? Where the study is done? Is that similar? The intervention characteristics, are they similar between the. Then finally, in the way outcome is measured, which is what we just discussed in terms of standardization. We use these characteristics to see if studies are. Then you also ask, are the studies that you have, are they reliable? Are they valid? Okay. So I think you might have had, you would have had that bias. So looked at this question of whether the studies are reliable or valid. You test bias. The risk of bias is less than you think results are likely to be reliable. Then after doing all this, have the data. You might have done all this, but the data that you're looking for may not be reported in the individual study. You need to also look at availability of the all these questions are affirmatively answered. Have good number of studies, comparable, reliability, validity index, or risk of biases data. You have data available. So in terms of steps, first step is you have to break down the question comparison. You may have a broad question, right? Very rarely you go with a very, very specific question that I want to compare tea with coffee. Right? You may have it, but very rare. But most often you start with a very broad question. So the multiple comparisons may be possible. You have to choose what are your comparisons. It's going to be tea with coffee. You're going to look at coffee and decaffeinated coffee. Is it going to be tea, some other form of tea? So choose what is your intervention, what is your comparison. Okay, that's the first thing. The second thing is you have to choose what's the population of interest. Study could have been done in any set of, so you have to choose whether are you looking at young males, or is it going to be middle aged, or is it going to be aged population? What is your population of interest? Correct? Then you have to choose your outcome. For this comparison, for this population, what is going to be the outcome of interest? I said even with in my example, we have two ways: calm, the dichotomous variable, also is a numerical score. You have to choose or fix what is the outcome of interest that you're interested. So in other words, you must have heard about SPICO, right? Patients, populations, choose the intervention and the comparator. Specify all this the meta-analysis. Once you do that, then you also, because depending on the outcome type, you choose whether it's odds ratio, you choose your measure of it. That's odds ratio, relative risk, or is it going to be mean? Then you go and collect data. You would have had sessions on collecting data, which is in itself huge process. You have to spend a lot of time looking at the individual studies and collecting data. You put that in a database, then you come to the step of statistically summarizing the data pool. So how do you do this? Summarize the result. What do you think? Number one, two, three. You also have we have definition of a static of some okay, plus. You haven't heard about random effects. Assume it. You don't know meta-analysis also. Let's say you are listening to the first time. What do you do? Sir, first, it seems like very intuitive, no? So you have by two table I told you, right? Calm versus no calm, tea versus coffee. Say 10 people have done it. those 10, stack them one mega big table. It's just arrange, line up the tables. Cells in A go with cells in second study A, cells in third study. Line up all that table. Calculate pooled odds ratio. Right? Possible or not possible? In one, maybe you attended some statistics classes, right? Or you did your averages. You have odds ratio from the first study. That is done. You have an odds ratio from the study. I'm has done. You have an odds ratio from first study. I can just take his odds ratio, her odds ratio. I can take an average of those two odds ratio. I can get an averaged odds ratio. If I do it, how would you criticize me? Say I'm wrong. Because, okay, why should I not? I'm asking the same question. Why? The same right answer, but I want to know why. Same part. Okay. Forest plot was when we did that together. Okay. Okay. I hear everybody saying, right? Sample size, sample size. Why sample size? Why can't I take, let's say his study has only 30 participants. If he didn't have much of a chance, let's say he has 2,000. Why can't I together? Sample size nothing to do. We can put both together. Why sample size? Study with 30 sample size. He has done with 3,000. What's the big deal? But how would I account for it? How? I agree with you. Tell me how. Study of? Okay, let me push you a little bit. Your study has 3,000 sample size. This study has 30. You got your results. Where in your results the sample size will reflect? In the confidence intervals, what do you expect his results? And what do you think will be his confidence? If everything else is same, right? But done same, everything is standardized. The sample size is different. It will reflect the width of the confidence. Has more samples, his width be narrow and his estimate will be precise. Because he has less samples, his confidence interval will be broad. This will not be. Okay, so what captures the effect of sample size is the width of the confidence interval. How many of you looked at what goes into the confidence? What decides the width of the confidence? Standard. That's okay. So if I want to take that aspect into, I will not be able to take that into account when I do this. That will be lost because one study has very small number, right? Precision of the estimates will not be as good as the other study. If I do either A or B, then I'm not weighting the study according to the information that it provides. One study provides good information, very precise. effect of the intervention is very precise. The other study doesn't provide that information. Studies, as I said, are equal in terms of the amount of information that they provide. One study is very informative. I can say this is the point estimate. It ranges between this to this, right? The other study says the point estimate is this, but it can be as low as this, can be as high as, can give you that information. You can't consider both those studies as same. One study which is giving you very precise information, and the other study which doesn't provide you that precise information. How do you take both? You do either this, then you are actually doing that. Okay, which doesn't when you think about it, doesn't make much of a we do, we have to do a weighted average. That average is like simple average, right? Add before you adding, you wait. Somebody is giving more information, you give the person little more weight. He's giving less information, you give little less weight. And you all said, how are you going to wait? Say what? You're going to wait by the standard error that goes into the what we are going to do in calculating the meta-analysis. Okay, so we are going to wait. We are going to wait by taking the inverse of the variance. Okay? It makes sense, right? If the variance is high, then the study should get what? Less variance. Inversely related, right? If the variance is small, if the standard error is small, then the study should get more. So we are going to wait by the inverse of the each study will get a weight. The weight will be equal to inverse of the variance. Once you weight the study, you calculate the weighted average. Just like how you do simple arithmetic average. Sum product of the weights with the individual effect sources you divide by the total of the weights in order to get the weighted average. So important part to remember is weight given to each study was of the variance. Variance comes from the calculation of the confidence, right? You look at the standard error, and then from the standard error, you go into the you take an inverse in order to the then naturally why we say small variance, small studies with small variance get a most weight, and then studies with uh, large variance get the. We have not done it. I mean, qualitatively, we can make this. So studies with most informative stuff. Okay, so this is an important thing. If you understood this, you get about half of terms of just conceptually what meta-analysis, right? So we're going to take an average of the effect measures. I'm going to take a simple plain average. We're going to do a weighted average. The way we are going to weight it by using the variance. The variance we are going to get it from the standard error, which comes here, right? Everybody, please. We're going to do an exercise. Give you 5 minutes. At the end of it, we'll calculate. First, explain the table. We have. Don't worry about what is the effect size, what is the variance. Don't worry about that. Hypothetical. We'll get the point across. Now, study 1, study 2, study 3. Okay? I have from each study, I have some effects. From each study, I have some effect size. I also got some variance. I want you to do fill up the rest of the works. Possible? I have given you all that is required. Given you X's, my previous slide, X is given. I've also given the formula to take from the variance to the weight. Now, I want you to see if you can fill up this. everything is here. But 5 minutes for you on your own. After that, I will go. Don't ask me whatever you fit. Based on it. Don't tell anything on your own. That's fine. That's it.
That's why we
Saying no inverse of the but All right. How many of you tried? Like you get that's all. Yeah, that's all. So let's look at it. See, I said the answer isn't always in the question. Right? Inverse variance. That's why you start. If you have variance, you want to take the inverse variance. First step. You do inverse of the variance, the weight, right? You have the weight, have the effect size. You know, take a product of those, right? If you do a product of those two things and you sum, get the numerator. Numerator will be reduced. You already have calculated the weights. Sum the weights, you get the denominator. You divide the numerator by the denominator. So if you start with the starting thing, the name suggests it's like first you start with the inverse. I also have an answer, but have the variance. You take the inverse of the variance and then take a product. Right? The percentage weight has been done, but you take the 2 divided by 1. The first study, the weightage is how much? People. Next one gets 25%, the next one gets 20. Total is. So the total sum of weight is 2. First study has get 1 out of the 2. The first study gets 50% weight. Second study, how much? 25% total weight. Third, okay. Okay. So if you get the how you get to the full estimate, you know, full part of doing is important. If you understand certain things, certain numbers you will understand, you can actually calculate. All right. So forget about this part. You'll come to know about the standard error. It was just like how we had a confidence interval for the individual estimates. We also need to have a confidence interval for our full estimate. For a meta-analysis, we also need to have a full estimate. If you're going to get a confidence interval, you calculate standard error. So that's the calculation. Why? I already multiplied, no? See, this is 1. 1 times 2 is 2. I'll just add up all that. Why? 5. This is what it is, no? Wi into x. Just summing up of it. Total. Hmm? All right. You want more time, little more time on this? You want me to go through one more time just to tell you how these numbers come? Right? So we start with the variance, right? We take the variance and we try to calculate the inverse of the variance. That's the first step. That's what this column is, the inverse of the variance. Okay. So 1 upon 1 is 1, 1 upon 2 is 0.5, 1 upon 2 is 0.5. Take a sum of this. So the symbol here stands for summing. Okay. So we take a sum of this. The sum of this is actually next step. We have the weight. We have the individual studies. So we are going to weight the individual studies. So this study effect size is 2. Because it has a weight of 1, it becomes actually 2. The next study also has the same effect size 2, but it has a weight of only 0.5. So it becomes 1. Same thing with the last study. It has an effect size of 4, but again a weight of 0.5 becomes 2. Now you add all this, just like how if you're doing individual average, what do? You add these things, isn't it? If you're just doing an average, you would add this. Because you're doing a weighted average, you are adding the weighted numbers. The weighted number is 5. And then you're dividing it by the total weights. 5 over 2, actually 2.5. That's why I said, don't worry about the effect size. Some effect size calculated. This is what is your pool value, pool result. When you take a weighted average, weighted estimate is about 2 point. Okay. So square root of the total weight 1 over that gives you a standard error. Don't worry about it for now. We'll come back to okay. So now don't worry. It's only think of it like a quantity that you need to give a plus or minus value. Pooled estimate is 2.5. You need to give something for the confidence interval. So if you have standard error, you can say 2.5 plus or minus twice the standard error with the confidence interval for the. All right. You need a break. So with the weighting, so I said one is the inverse variance weighting. That's a common method. But also you can choose, especially if you're using RevMan or any program, you would have different weighting weighting methods. One is called Mantle-Hansel. If the cell counts that you have, if those cell counts come from rare events, right? Event rates are rare, then we would use weighting scheme. So the weights come from this formula. So it's not just inverse variance, calculate the weight from here. Similarly, if effects are close to 1, so if you have odds ratio or relative risk close to 1, you use what's called as a Peto method. Again, weights come from. Don't worry about this. Just to say that there are different ways in which you can weight the studies depending on situations. You have a rare event situation, number of event small. over the total, then you would use sample size. The effects are close to 1, they're not large. Finds of the rare events. Then you also have an important choice to make. You have to choose fixed and random effects, especially when you're going with the RevMan software. While you're actually putting in these things in RevMan, while you're in the stage of analysis, after choosing the outcome type, after choosing the method of weighting, after choosing the effect measure, you need to choose whether it's going to be effects model or it's going to be a random effects model. It's a very important choice related to the concept of. Okay. So now going to that. Let's say suppose you have done that. How do you represent? So all of you by now would have seen the forest clause. Say you have after the meta-analysis, you want to represent all the study graphical way. Use a graphical. So you have the x-axis, you have the scale for the effect measure. What's in the horizontal axis is the effect measure, right? Means it could be odds ratios, or it could be relative risk difference, or it could be mean standardized mean. Then you have the y-axis. This stands for the right, and where you place the y-axis, whether it is 1 or 0, will depend on the effect measure, right? So if it's an odds ratio or a risk ratio, you put that uh, vertical line at 1. But if it is risk difference, mean difference, that line on basically conveys that that's the line of no effect. Then you take, what do? You would quote for, okay, where does the first study comes in? So a square box represents that measure, whatever it is. If it's a relative risk or an odds ratio, that box here says about the odds ratio or the whichever effect measure that you have chosen. What does this line suggest? Confidence. So you have a plus and a minus part for the point estimate. That shows the confidence interval for the first. Right? But then you could have all the studies coming in, study, the third study, fourth study. See that all the point estimates are different. Right? Some of the point estimates this side of the plot, some of the point estimates this side. Also have confidence intervals, right? Almost like a forest. So then you look at diagonal. What does the diagonal say? Yeah, diagonal diamonds. Diamond usually stands for the width of the diamond is what comes from the standard. I have a confidence interval for the right. This is the part I mentioned while first slide about what is meta-analysis. I said meta-analysis is an optional part of practice. To do meta-analysis, just that you don't get this part. Else, put a quantitative historical summary and overall full picture of instant. Then you try to summarize. What meta-analysis does, in addition to all of this, is like, okay? All right, so this what you see in the RevMan. So if you have you been using RevMan, the practicals? So in the RevMan practicals, you would see studies listed out here with the author and the years, and then you will see intervention comparison, I and the part. Then you have sense and total, right? So that means you have the numerator and the denominator, right? The 2 by 2 table. So look at the 2 by 2 table, you get first cell and total cell. This is important because when you try to put in data, no, RevMan, You put all the cells, even put A and so you get those two things, and then shows you the weight, right? Calculated a couple of slides before. Weight comes from the first means from get the weight, and you also calculated the percent weight. Total weight is 100. Get percent weight for each of the after the percent weight. Let's have this right. I just do the three ways in which you can weight. This Mantle Hansel and the inverse variance. Here they are used Mantle Hansel to calculate the weight. This is the relative risk from along with confidence, right? You have the forest plot, which I just showed you now. That individual studies with the risk ratios in fire and the confidence interval as horizontal line. Then you have the pool meta-analysis first diamond. Then this part is where I haven't told you about, and this is what you're going to discuss coming up. Okay, this is about other part of meta-analysis that we're going to talk about heterogeneity. What is chi-square estimate of heterogeneity? What is chi-square estimate? How do we deal with subgroup analysis? How do we comes? You have done that part. You're happy with all the calculations. You do what's called as a sensitivity analysis. Very important part of meta-analysis. Where try evaluate the impact choices that you made while you are doing the analysis. There are many places where you've chosen one over the other. Right? You might have chosen fixed effects over random effects. Random, or you have included one study, You're going to choose, you're going to look at what is the impact on those decisions. Right? Do the results actually change when you make those changes? Suppose if I move from fixed to random to the full estimate, very different. Or if I exclude one study, then I run the analysis. Do I get? So you test for how robust are your results, and if the results are still the same, then you're pretty confident. You say, regardless of how I play around with the studies, how I play around with this, the results doesn't seem to very much. On the other hand, if the results change a lot, then more cautious. Can't just make one statement about this exam. Can't just say the interventions. Have to uh, add 2 or 3 more lines down and explain the other things that goes with it. Right? So I think this is a good place to stop. Yes, so one whole you have 10 minutes if you have any questions. You come back from lunch. Afternoon. If you're doing prevalence studies, have you heard about MedCal? MedCal is one software. It actually gives you a 15-day free trial. So you can actually, if you're ready with everything, then just download the free trial version and get it done in a week back. Afternoon. Any other questions? You would have a data extraction like an Excel file, no? You just so, so what we the usual thing is, so you'll have, let's say suppose the data extractor, all the select studies, I'll go through the individual studies. I fill up this Excel database. I'll say study number one, patient average age, whatever your form, I'll fill up everything, including the data. I'll say how many survived, how many died in the first arm, and similarly how many survived and how many died in the second arm. Right? So I'll have one row for each study. So likewise, if I have, let's say, 20 studies, I'll have 20 rows in my Excel database. Right? Now, when you come to RevMan, you can actually take that number of rows and this thing and paste it in RevMan software. So you have to convert the median to mean, or you have to look at, there are ways in which you can convert the median to mean and then look at the standard. You would have given IQR and use the IQR to convert it to a standard deviation. Yeah.
Like what is the outcome? That's what I was trying possible, but now of it. The way study that samples are media. That is the how I
Yeah, yeah. Uh,
information by the I think also RevMan did.
couple of ways you can do. One, it depends on what you think about it. So if you think the standard deviation in the control group, the natural standard deviation, then you divide it by the standard deviation in the control group. Because control group doesn't get any intervention, so we expect whatever variation is there is actually a natural variation. So for now, all our weight calculation is totally on not it's not directly on sample size. See, if it's directly on sample size, I can divide by sample size, right? I'm not actually dividing by sample size. I'm actually dividing by the standard error, the function of sample size. So it takes a few of the other factors also into account when you look at just the standard error. It's not. It takes a variability, no? It takes the variability codes for many things. Actually takes if it's a poor study, you would expect the variation to be more, right? Even all the other factors that you mentioned, if it is done poorly, you expect sort of variability. That's what it takes. I'll come to it in afterwards. Yeah. Okay. Oh, that depends, right? So that's more of a research question, clinical question. Suppose if you want to go all the way to the first study that is published, if you want to go from the first ever study done and then want to track historical, to do that. But if you're just looking at last 5, you reside in your
Ask that question.
all points. And
comparator has this as well as over analysis. So, and what
Good afternoon, all the delegates. I request everyone to check their attendance sheet with signature in all the day 1, day 2, day 3, day 4 signatures. And at 2 p.m., we'll be cross checking the spellings to be written in certificate.
Right? So I have sent you, Saikat has sent, I gave it to him, there's a PDF document on converting effect measures. It's a very recent one, 22, 23. But as you pointed out, you need the distribution. They also give you links to calculators. Put in your median and your IQR, and it will calculate approximate mean and standard deviation. So it will be sent to you. I don't know how he sends it to you, WhatsApp or just check and see. You find the paper there.
We would start from the, we stopped here, right? So we said this is the forest plot. So the different parts in the forest plot. And then we said some of the things which are there in the forest plot which we haven't seen are directly related with heterogeneity. So we said the heterogeneity, we first see what is heterogeneity. And then we would see about the chi-square test. And then we will also look at chi-square, which would assess heterogeneity that is present. Then we would look at how do we deal with heterogeneity. So that's the two parts that it's need to go through to them. We also looked at sensitivity analysis. So this is where we were. So when we say heterogeneity, we mean difference in effect sizes between studies in a review. So if you, in a review, if you have, say, a sample of studies, say 10 or 15 studies, and then you notice that there are differences in the study effect estimates. What we mean by this variability in the effect sizes from different. So then we think about what could actually be factors that could potentially cause this variability. What could actually cause this heterogeneity in the effect estimate? So the first aspect is, we call it as clinical heterogeneity. A real world could come up because of various clinical factors. A real world could say, okay, there is a difference because the populations are different. Study was done in different populations, and that is why there is a difference in it. That could be one. Or you could say because the uh, intervention is implemented differently, or the intervention is a little different from one study to the other. It is not the uh, same protocol for the intervention. Okay? So if you have those kind of factors, those are real study level factors, and if you think the differences are due to those study level factors, call them as clinical. Okay? So that's the first level. Look at studies to see what could potentially cause differences, what could potentially cause this variability that you think it's because of these clinical factors attribute that heterogeneity to clinical. The other one, equally possible, is methodological. So when you have different studies, methodology wise, they are different from one to the other. Okay, so two randomized controlled trials. One randomized controlled trial was double blind, other one was open label. Okay, then you would expect the effect estimates to be different. Isn't it? So when you have a double blind study, you expect the effect as more precise than open label. So likewise, you may have different characteristics of the study in terms of its methodology. And so if there's a methodological difference, then you can attribute those things to heterogeneity due to methodology. The last one is what we expect, usually even without any heterogeneity. If there is no methodological or clinical differences, there will be some difference, regardless. Even if all the studies are doing the same thing, there will be some differences which just are what we expect. So if you see a difference, base the difference proportionally to these. Some of the difference clinical factors, right? Some of the differences could be methodological. Some of them investigate why there is a difference. It's fine significant. So what it adds to it is when you understand more about the intervention, more about investigating this, sorry, then you would say, okay, the intervention effect varies because you'll be able to list out helps gain a good understanding about how the intervention it works in a particular population. works in some of the variation as clinical variation, but rather it's actually methods. So you can say, okay, some of the variation is attributed to how the intervention. Okay, now we go into models by which we try to pool the results. First one is called as a fixed effect. When you try to pool or when you try to combine these, now I said two choices. One, you can have fixed effects model or random effects. First model is called as a fixed effect model. What we mean by fixed effect is we assume effect is actually fixed. It doesn't vary from one study. Okay? We assume that the effect is actually one effect. There is one single true effect of the intervention. There is just one thing, one effect that we are trying to estimate. And while we are trying to estimate, there is some difference, and this difference is random. So all studies are trying to estimate one effect, okay, which is what we consider true effect. While each study is estimating it, that is, they're estimating it with some error. Okay? That error is actually due to, we call that as a random error. The idea behind fixed effects model is there is one single true effect. There are 10 studies. 10 people here are doing a particular study. And if we assume that the effect of intervention is one single, if there is one single estimate, then we are going by, when I say one single estimate, what I mean is if there is differences are no particular real reason why the effect estimate vary. Effect estimate comes because the underlying assumption that we make is that there is one single, that's called as the fixed effect. So you notice that this is the true effect. This is the observed effect from study I. There's a difference. Difference is due to this random error that each study has some error. But error is what causing this difference. Some of them are positive, some of them are negative. That's what we observe, depending on what's the difference. Okay, so when I mean a fixed effects model, I'm assuming the observed effect size is a function of the true effect size plus some solve. Okay. Now let's go to the other way, where you can assume what if the effects are not fixed? What if you say there is no one common, but each study is actually estimating its own true effect? Okay, there is one study is estimating its own true effect. Other study has its own true effect. There is another study own true effect. So it's not one true effect, but actually a distribution of true effects. So earlier we said there's only one true effect. If there is a difference, the difference is actually due to chance. Now we are saying there is no one true effect. There's actually a distribution of. There's actually a distribution of. Now, if there is a difference, why there could be a difference? There could be a difference because of two factors. One, there's usual random variability that earlier, which is it comes from the effects, but also this effect can vary from the average of the right. So now have a distribution of single study estimate could vary because of two things. One, it could vary because of the random variation. How it could vary because there is a distribution of So if you account for two sources of variability, there's one which is called as the chance variability, or could vary because there is a distribution of effects. No single effect. You are looking at a distribution of effects. So maybe you sampled it this side, so it varies from the average. Okay. So when you are doing random effects model, you want to account for both these sources of one. There is this difference which comes from between the studies. Then there is a difference which comes from within the right. In the fixed effects model, we have only one source of variation. Then we have this conflict. The observed effects varies as a function of true plus some random error. Now we are saying it's not just a random error, it's some random. Also have been studied. You understand this important thing. So function call that. On the other hand, how do we effects out the size of the but when you random effects have to think about parameter capture is very important. This, as I said, so the random effect have the random there is in a specific expression that there are one thing. So how does this matter? Where does it where does this effect comes in when you are actually doing the meta-analysis? So in your fixed effects model, you take weight as the inverse of one single component of variance, right? Because we assume there is no mean study variation, all the variation is because of chance. Only account for that in our ways. This is what we did this session. Right? We calculated weights based on variance that we calculated. We use them as. But when you do random effects model, we have the random variation. That's a variation within the group. But we are also saying that there's a variation between the studies because there is a distribution of effects. Each study is estimating its own effect. There's a difference in effects. We want to take that also into account. So when you are calculating weight, now you have to calculate two things. One, you have to calculate the within study variation, which you have estimated from your standard errors, we have to calculate between study variation. Call that as tau square. Now your weight is inverse of both these variances. Okay? So in the fixed effects model, you have one parameter less to estimate. You don't need to worry about between study variation. Why? Because you assumed all the differences that are there are plainly due to there's only one single true estimate. But when you are doing random effects model, you have to calculate this between study variability, because now you are saying that there is no one common effect, there is distribution, and we are trying to estimate average of the distribution. Now I want you to go back to the definition of meta-analysis. Right? You remember anything that comes to you from the definition of meta-analysis where we slide 15 slides before? Average or common effect. Think it is common. There's only one true effect called as a fixed. But if you say it's an average, very different from common effect, right? Then it's actually a random effect, right? You see that? So when you say a common effect, think that there is one single true. When you say mean there are many true estimates. I want to estimate the distribution, calculate the means. Already have the mean. Now I have the distribution x. Calculate what's the average. You are doing random effects model, very different from fixed effects model. Okay? Because in one, you are estimating a common effect. In the other, you are estimating the average. Okay? So you have to make this decision while you are actually doing your study, looking at state of a protocol, what type of effects do we expect the distribution, all the studies to be in one common effect, or do you expect something different? And you want to account for that. If you think there is a distribution of effects, then you have to random effects. How to decide? Next. So you have here, this is the forest plot. Have on one side you have the fixed effect model. You have on the other side the results from the random effects model. Right? So what do you see? Both are similar. When you say both are similar, you're looking at the pooled effect is similar. Why do you think the pooled effect is similar? Okay, so think from what we spoke about in the last two slides, from the heterogeneity aspect. You think there is considerable variation in the studies? Considerable variation from the forest plot. There is a lot of variation between the studies. Okay? If there is no variation between the studies, in our weighting, what do you see? Right? So in our, if there is no difference between the studies, right? If there's not much of heterogeneity, then what would we have for the tau square component in our weights? Close to zero. There will be some difference. Difference is going to be close to zero. If it is close to zero, the weight from the fixed effects will be not exactly equal, but will be close to what the weights that you would get from the fixed effects model. Right? So if the weights are more or less same, then what you get as a pooled estimate will also be more or less same. So what one way of concluding this, or one way of interpreting this, in the absence of significant heterogeneity, the results from effects model similar to the random effects model, because the estimate of tau square will be close to zero if there is no significant heterogeneity. Okay? Okay. Not much heterogeneity, tau square is close to zero, no difference in weights. Analysis would probably give the same result. What about this? How do you think through this? So if you notice here, this differences, right? Not so much. There is some level of difference between the studies, right? So if there is some level of difference, then you would see that reflected in the weight, right? Because you will be adding an extra component of tau square in our weight estimate. Depending on how large the tau square is, the weights are going to be different between fixed effects. Right? I also pointed out the weighting for a couple of studies in the fixed effects model, then waiting for the same studies into the random effects model. What do you notice? What do you notice? So if you say these two studies, right, which the confidence interval is too narrow, right? They may be large studies. So because they are large studies, the weight is totally absorbed by those two studies. Right? So they are large studies. But when you come to random effects model, there are two components in weighting the random effects model. You just don't have only the within study variation, but you are also looking at the between study variation. The within study weight is balanced by the between study, right? So the weight gets distributed more, little more conservatively, right? Not just the big studies get more weight, but depending on how the between study variation is, it balances out how it weights the. Okay? So you look at weights are distributed accordingly, then that variation is also absorbed the pooled estimate. Now, when you have pooled estimate, because you have two sources of variation, confidence interval is little more wider as compared to what's the confidence interval get from the. Why? Because you have one other source of variation in your. It could be, could be that. I'll get to that. Could have totally. That's what I was trying to say. Because when you have one additional source of variation, that source of variation is absorbed into your pooled estimate. So here you have a very narrow estimate because you have taken only one source of variability. Here you have added one more source. You have between source into it, so that the confidence interval is little more wider than what you get from the. Okay, so people often ask this question: should we use fixed effects or use random effects model? And people often think in terms of you look at the data and if it's heterogeneous, then you do random effects model. Not heterogeneous, you do fixed. But usual be better if you do it without looking at the data, but then having an understanding of how the effects are expected to be distributed twice. Then you also give, okay, we'll do a sensitivity analysis, and then you check for random. Because even if you do random effects model, what it would do is probably absorb heterogeneity in the confidence interval. It doesn't explain heterogeneity, right? will only kind of improve the, can only increase the width confidence interval. It doesn't explain why heterogeneity is there in the. So in terms of whether you would use fixed or a random effects model, you need to think about heterogeneity prior, then make a choice on whether you do a fixed. But once you make a choice, what you're saying is that in fixed effects, you're saying there's only one true effect. The intervention has just one true effect, right? And it's a common. Studies all share the same. There's a difference. The difference is actually due to when you do a random effects model, you're not saying there is one common effect. Each study is having its own true estimate, right? So there's a distribution of effects tested in average distribution. Okay. But more in terms of heterogeneity, I don't want to show you formulas, but I just want to get you a feel for how you can get an understanding of heterogeneity. So if you have these two plots, what would you say is heterogeneous? Plot A, one here or there? This one or this one? Why? If I look at the first one, I'll have a go. You have a go at it. Why first? This one, right? This looks heterogeneous. See, if you look at this one, some of them favors the treatment, some of them favors the control, some of them are in the middle. So favoring treatment, not favoring. So he would say this is actually. What's your? Why do you say it's not heterogeneous? Huh? Well, it's studied. Not by the what's the visual. All right. So if you look at here, do you think it's heterogeneous? That's a good point. So when you can actually look at the point estimate say about heterogeneity, or you can the then you can here we actually look at the overlap. There's an overlap in the confidence interval. There's no not looking at the point estimate. Okay? We're looking at the size of the confidence intervals and whether they are. If there is the overlap, they look for the point estimate. Okay? What about this? Finally, so here if you look at point estimates, you may think this one is more heterogeneous because some of them are in this side, some of them are in that side. It's not. You have to look at the width of the confidence intervals and see whether they overlap or not. Here they all kind of more or less overlap, but in this case, not much overlap. Like some of the confidence intervals do not overlap with each other. I think the heterogeneity is present more here as about this. In which case, heterogeneity is more important to consider. One. Why not this one? In this case, it's important because though there is heterogeneity here, they're all in one side of the plot. There is heterogeneity, but is it serious enough for you to consider? Because they're all in one side. They're all kind of favoring the. There is some difference. The differences are on one side. Here, it's not the case, right? See, here the heterogeneity is important. Okay. So here it's qualitative. No, you have to look at it. In this case, it's important. In this case, all of the effect sizes and the confidence are one side of the plot. It doesn't. It doesn't. Heterogeneity in this case is not going to be huge difference. Confidence intervals over that. The previous slide is about where you look for heterogeneity. Do you look for heterogeneity in the point estimates, or do you look for heterogeneity in the confidence interval? The point there was to say, don't look for the point estimates, but look for the confidence. Here is to exact opposite of that. We're saying, okay, look at where the direction of it is. So if you see everything in one side, in that case, heterogeneity doesn't make much matter. We have to do something about investigating that heterogeneity. Right? What we studies effect as different. That's what we saw. No, this study estimate is here saying treatment is better, and in this one, the study estimate is saying control is better. Okay. But this is only an estimate from that study. Normally, you have to interpret that estimate along with the confidence interval, because it could be that the estimate is here, it could be that it's there. Right. So when you look at this, all the confidence intervals are overlapping. That's why he said this has got less heterogeneity, not much compared to this. When you're comparing this and this, got less heterogeneity because here the confidence interval overlap between this one and that one is not there. That is what he was trying to make. Next slide. Now in this one, you apply the same principle, right? Confidence intervals are not overlapping. Here, confidence intervals mildly not overlap. So there is heterogeneity. But the question is, which is more important to consider in making your decision? So there, what you have to look at and say, what is your conclusion from this entire forest plot? This conclusion is what? You don't know. Inconclusive. Why is it inconclusive? This one says treatment is that much better. That one says control is that much better. You're really confused. So I always look at it because we will relate this to grade. We have to grade the evidence based also on heterogeneity. So what my question here is, if it was here, would you use it? Would you use this intervention? If it was here, the question is you're confused. So if you're confused about whether I'm going to use it or not use it, whether it's the upper end or the lower limit, that is imprecise as far as important heterogeneity is concerned. Here, what is your pooled effect? If it was here or if it was here, will you be confused? No, I will use it. But there is heterogeneity. But when the heterogeneity is all agreeing that one treatment works, so whether it was here or whether it was here, it is important. All you got to look and see is what is the minimum important difference. Right? If the minimum important difference was here, right, then you might have doubts. But you don't have any confusion about that. Then this heterogeneity need not be a reason for you to not doubt the result. There is heterogeneity, but it's not important for you to doubt. Then repeat this again tomorrow. So now you want to have some estimate of heterogeneity. So one thing you could do is do an actual statistical test. We call it as a chi-square test. As usual, you start with a hypothesis and you say your null hypothesis is that all studies are homogeneous. And then you look at the data, and at the end of it, you get a p-value. If the p-value is significant, you say that you reject the null hypothesis and say that these are non-homogeneous. So the forest plot I showed you at the side of this chi-square value and then associated p-value. You look at the p-value from the test, and then you try to make an conclusion about whether there is significant heterogeneity, statistically significant heterogeneity present among the studies. But the issue with the test is, as usual, most of the statistical tests require enough number of data points. Right? You need to have adequate number of studies going into the test for you to be confident about the p-values. Right? So if you don't have in the first place too many studies going into the calculation of p-value, then the power for the p-value is quite low. Right? So you may say there's a lot of times where you may say there is may not reject the null hypothesis. Like there may be a significant heterogeneity, but your test will not pick up the heterogeneity. Okay? So that is where I've had a slide in terms of how many studies to include. We have a sample size problem in the channel. If you're thinking from heterogeneity point of view, then you need to have some reasonable number of studies for you to really trust the results that comes from the. Okay? That's with the chi-square test. So there's also an alternative to chi-square test which can be more informative than the actual p-value. Use an I-square statistic that comes from the chi-square. So you take the chi-square instead of doing it as a p-value, you take the chi-square and then convert that into a Q statistic or an I-square statistic, which is separated qualitative. So instead of looking at p-value and saying whether there is statistically significant heterogeneity or not, you would use that value to calculate this I-square and comment on how much of heterogeneity is present above and beyond us. So you get a measure of a quantitative measure of heterogeneity, and then you can kind of interpret it saying different bracket. If it is 32%, consider that as low, or if it is in a particular threshold, then you moderate. If it is above the threshold, you consider that. But again, a little hard even there because you have to make an interpretation from the heterogeneity present, then to kind of categorize and say this is significant or substantial as against moderate or low levels of heterogeneity. But it's much better than what you have in terms of S-square. So now we have quantified presence or absence of heterogeneity. Now you have known that okay, there is heterogeneity both in terms of chi-square and also I-square statistics. What could cause difference? Okay. So if there is a difference in effect, what would be those factors that could modify, that increase or decrease the effect over the average? We need to identify those interacting modifying factors. Okay, one of the ways we could do is by using what's called as a subgroup. Right? So if your factor that you have taken is a categorical factor, right, which means that factor exists in categories, two or more categories are there, then you could do the subgroup analysis, see how the effect size varies over the subgroups. You can test whether that variation is, whether there is an interaction of variable, just like how you would do in an individual randomized trial. If you're doing an individual randomized trial, you finished your first primary outcome analysis, you said the outcome, the primary outcome, this is the effect test. Given that, additionally, you would do subgroup analysis to see if there are any subgroups. If you pre-specify them, you would test whether how the intervention works. see whether the intervention works in male. Does it work in smokers, non-smokers? Right? You may have a few subgroups which you would have specified, like to test, like testing across those. Similar thing here, where we take the overall pooled estimate and we set it in listening, modifying it. So you could look at example. This is one of the examples, Cochrane, where we said overall there is an effect. Okay? The outcome is for the chronic pain. And then you also have a subgroup analysis. We have done a subgroup in terms of studies which had used only one single dose. Then there are studies which have used two doses. Okay? And overall, if you look at, there was a significant, just the overall effect, the I-square statistic is about 76. Okay? So you may think, okay, if I stratify or if I do subgroup analysis by dosage, single dose studies versus multiple dose studies, does that explain this heterogeneity of 76%? Okay? So if I take studies that are only single dose as against studies that are multiple doses, and if I pull those studies separately as from, does that explain some amount of heterogeneity? If it explains, what you would expect those studies within that strata similar, right, as compared to studies in the other strata. So you would expect the I-square value for that particular subgroup reduce compared to the overall I-square value that we, just like usual subgroup. Within the subgroup, we expect the units to be similar as compared to between the, notice the value. So you take single group or you take multiple, I-square value is, right? Also, if you look at pooled estimate for the first single group studies, also for the multiple groups, you see overlap in the, no significant difference in the effect estimate in the, so basically in both ways, factor that we have chosen explain heterogeneity that is present in the, okay. We see a significant amount of heterogeneity. We thought dosage, number of intensity of dosage would make a difference. We look at subgroups, we choose set of studies, doesn't seem to explain the heterogeneity. This is another example where you can see the grouping variable that we have taken and how it explains the heterogeneity that is present. So if you look at here, I-square value is significant, total I-square value, 52%. Then you take dependency, the level of dependency. We explain that variability present in the effect estimates. Okay? So you divided studies which have taken high dependency smokers and studies which have taken low dependencies. Then you calculate an effect pooled effect size for those studies, calculate a effects. Look at heterogeneity within those studies. The I-square is only 13%. What you have done is you have used variation that was there. You see that this particular variable explains heterogeneity. When you look at low dependency smokers, variation is almost, here in this case, by doing subgroup analysis, factor the level of dependency on smoking, you could explain heterogeneity that is present in the. Now you know that the intervention works differently for low intensity smokers as against intensity. This is one of the reasons why high levels of heterogeneity in the. Okay. Now we spoke about categorical variation. You can do a subgroup analysis in stratas. They have to be in groups. What if you have a covariate, not a categorical variable, but a continuous variable? So if you have a continuous variable, you have few other covariates. It's not one or two covariates, but you have a set of covariates. Just like how we do in our primary studies, we would have to do a regression. Right? We would have to do a regression analysis. See how the effect sizes vary as a function. So in the like how in ordinary regression analysis, you will have an outcome variable. You will also have a set of independent variables, right? A dependent and an independent variable. Then you will take a function and model how these independent variables affect the dependent variable. Same context. So here the outcome of the dependent variable is the effect size, and your independent variables could be any one of your covariates. So here in this case, it could be an age. So you could say as a function of age, how does the effect sizes, right? Or you could say one other covariate is continuous. Say how does as a function of that, how. Okay. So you go from subgroup analysis to meta regression, move away from one categorical variables, status, or if you have more than multiple, not just one or two sub, you want to look at together all the factors together. So what some of the problems in terms of looking at heterogeneity? One, you may, I mentioned it slightly before, you have to specify some of the work. Just like in primary analysis, you have a tendency to for many factors, and that factor is related with and effect sizes. Problem with data dredging, if you're not clear about it, it's a good practice to actually mention those factors. If you have n number of factors, it's really possible to get all those factors. And then you also have to, in your protocol or in your document, you have to specify kind of give a rationale for why you're choosing factors. To kind of prepare so that the results are not they don't come back, they don't come out because you're exploring the data. Right? So and you have a hypothesis for all these investigation features. Then comes publication bias. So you have to kind of investigate publication bias after come up with an estimate. You justify it is not a biased estimate. So usually we investigate using what's called as a funnel plot. So if you look at in the horizontal axis, you have effect measures. So it could be either an odds ratio or a relative risk or whatever effect measures on the horizontal axis. And then on the vertical axis, you have some measure of precision. Right? So here in this case, it's a standard error of the effect measure. So it's an inverted axis. So if it is here, if it's in the top, you have a high precision, high measure of precision. And as you come down, there's much variability, right? Imprecise. So ideally, if there is no bias, then you would expect this kind of pattern where you see an inverted funnel. If there is no publication or reporting bias, you would expect kind of a distributed at the end or at the lower scale. But you have some studies, you have some studies which are positive and some studies which are negative, right? And then the range of effect sizes if the study size is small. If it is imprecise, it also means standard error will be more when your sample size is small. So here at the bottom, you are looking at study. If there is no publication bias, you would expect positive studies small, also expect negative studies. Okay, so what happens in the presence of publication bias is small studies that are negative will not get. Okay, so if there is no small studies, no negative small studies, have an asymmetrical. Okay? There's an asymmetrical pattern that is an indication of publication. So you plot this and then you look for pattern, and if you proper funnel plot, funnel inverted funnel shape, symmetrical shape, then it is studies miss white circles are studies which are missing out, then it means that studies are missed out. Some of the small studies negative, which indicates that there is a okay. So what do you if there's a publication bias, then you show that if the publication, then you may also have to say how do you deal with publication bias. Some instances you have to show in your protocol stage where you look for files pre-registered databases have some way of accounting but not published. Still you have data on those studies. You can say, okay, we are covered denominator pretty first. The other option statistically, if you're missed out on that, the statistical option is that you can do some kind of an imputation where you can fill in the missing values. Right? You can say, okay, these are studies which are missing because they are not published. So can we impute those studies so that we can actually correct for the publication? Okay, there are some methods that are there. The standard methods, but there are a lot of problems with those standard methods as well. So you can use one of those methods and say we have adjusted for our estimate is adjusted for. Okay. Yes. So I'll get into some of those protocol considerations. So I said we started with outcome data type. Right? Depending on the type of outcome, you choose your effect measures. Then from there, you go and do a full analysis. Have a random effects. Just what's the problem in what's the discussion on fixed rules. Once you're done that, then you have to address heterogeneity. You can either move heterogeneity up or down depending on this way, no? That you have to have an idea about heterogeneity first. That's fixed random effect better about it, but I can see you can see practice can be, as you mentioned, like you can say, okay, we will look at the data, we will see whether there is significant heterogeneity present. And there is a significant heterogeneity present, then you do random effects model. If it's not heterogeneity, one way. The other way is that from where I told you about, you think about the effect sizes. If you think there is a common effect, right? If intervention has one single common effect, fixed effects model. There are ways in which you can, within the fixed effects model, also you can investigate. Not that if you do a fixed effects model, you can't investigate. Within a fixed effects model, you can investigate heterogeneity. If heterogeneity is your concern. On the other hand, if you think it's not one common effect, but it's a range of effects, distribution of effects, not interested in one common effect, overall effects. Why do you ask? What context? Ah, Which mixed effects is a combination. is specific. Right? So then you look at assessment of heterogeneity in terms of square and chi-square. Talked about subgroup together, the data considerations. The order may vary, kind of, or how you kind of see components in the but model may vary for different. So one outcome when you have the outcome. Okay. So it is not different from the primary research. Needs a lot of people, right? One person will not be able, or one or two people is very difficult. So you need a group of expertise in domains who are good in searching and selection. People are coders, and you have the methods part of it. You need to address on the method part so that it is done really well and correctly. Okay? What we just about. So we go into an example. You know how you do it. You have a printout, but so this is a study which is continuing with my T. So this is a study published in PNC Public Health, looking at the effect of T, meta-analysis. Okay, so I also highlighted something about handling the. So you're looking at non-pharmaceutical public health intervention that could be useful for epidemics. So they did a meta-analysis of randomized controlled trials and prospective studies to look at the effect of gargling with tea on the prevention of influenza infection. Okay, so that's the kind of study question. So at both randomized controlled trials, also prospective cohort study, look at the effect of gargling with prevention of influenza. Outcome is infection. Have intervention in gargling with some competitor or in a so they have the strategy and other things they track. Then finally show there is risk of influenza with gargling and with placebo water. Those who do not gargle use effects. Relative risk 0.70, confidence interval range is 0.5 to 89. Then equivalent and then random effects model 0.71, 95% confidence interval range is okay. Then they say fixed effects model had a better quality of fit, random effect. They would actually go with the fixed model. Okay. But you can read the paper, but you can. Is it possible for you to just pull up and read for 10 minutes and then I have few calls? Now that doesn't matter. It's about model. That doesn't matter for whatever we have discussed for now. But I'll explain to you that little later. That is what I want. It will take 5 to 10 minutes. For very it's more complicated stuff in it. About 5 to 6 studies. I hope you read some parts of it. I kind of skipped right into the methods. Did you figure out what type of outcome variable they have, like ours? Let's mention influenza S versus which among the effect size was relative risk odds ratio, right? I think they chose relative risk as well. Then cleaning process that they had their studies, and then they had to quite a bit. Finally, they had about 5 eligible studies. After 5 eligible studies into the analysis, from randomized perspective, the same. Then the table, the database table. So you have the study, publication, year of publication, total sample size, some baseline characteristics. But we use it for our subgroup analysis. There is quite a few number of studies. Then you can look at them for your either for your meta regression or for your subgroup duration of the treatment or the trial, type of study. So when you look at it, do you see any heterogeneity? One could be methods point of view. You have some studies which are RCT and then you are prospective cohort study. Find both the biological, clinical heterogeneity. There's a few baseline age and ages in one of the studies. Yeah, definitely variation in terms of using about gender. That looks fine. So this you kind of look at this table, baseline characteristic table, just give you some idea about heterogeneity, right? You look at it and see how heterogeneous. So depending on this, which effect, how do you think we go about combining the results? And second plus seven. So one you can first it depends, no, if you're on how you want to go about it. Let's say for instance, first I would look at then I would do a subgroup and looking at randomized control trial one perspective kind of then see is there a difference. So here so you're saying we would go with a random effects model because you think there is significant heterogeneity both in clinical also in biological variables. That that how all of you so anyone of you think its effects would work? Yeah, variation. When we are looking based on data analysis plan, they're saying we're going to use Mantle-Hansel method for fixed effects model and a random effects model. Random effects will be fitted using fitted maximum likelihood estimation. Okay. Then they are going to use results will be exclusive relative risk and confidence interval. Talked about chi-square test and where the Q comes, and then you take the I-square statistics for the random effect model. They said P not equal to 0.05, but say P less than 0.1, we considered the statistical significant. They interpreted if anything more than moderate to large quantities. They also tested someone was about AIC, if you have a model. You can also test how good the fit of the model is. Criteria statistics, one is AIC, and look how those values are, and then you decide on which of the model kind of better fits. Yeah, but it's more of a statistical thing than anything really significant there. Then you look at publication bias, that funnel plot. I also did Edgar's regression analysis just for that. Then significant publication bias if the intercept is that is what is reviewing the plan, any problems. Whatever is it is PubMed from 9 rest other databases that whether facing this problem with the search strategy. Okay, with the statistical plan, we have addressed all the things that we said. Think about it when you're doing writing up protocol. They covered everything, or is there anything if you're looking at it and you say, oh, this is that's the okay, so you are happy with too much, little too much. What I'm saying. The way of testing model is kind of like going above the F, not different. All right, so if you're all okay with it, then a lot of people are asking about software. Good look for that. I'm started and go and see software. They have used R, then for detection R, what is it? Then I Google up the package, see how good is the documentation for the reason is you have RevMan, and then RevMan covers quite a lot of things, right? And makes it much, much easier for someone to do the analysis. You can feel it when you're doing analysis with the RevMan because the data, things popping up on your very active, no? Doing analysis in RevMan. That's not the case with say other software. You have to do a bit of work. It has both plus and minus. So if you're doing in other softwares, that what's the documentation for the package or for the program that's it. Okay, so then they have this plot. So for the 5 study, the scale that one here would mean no difference, right? Because it's a relative risk. Not expect the vertical line on 0. So you on 1, then the evidence of statistical at the forest plot. We looked at few forest plots, right? As a box example, we're looking at it. Where do you think this one would fall? All overlap with each. They're also mostly on one side, right? Right? is there an evidence or not? No heterogeneity, right? But you see, one thing that was study to show the clear effect, right? Probably the first one is just a edge, right? But when you come all the studies, you could actually the intervention. What we say, why we are doing meta-analysis. One of the reasons power, and we also said precision, like we're able to detect effect sizes with the numbers, gets more data with the number of. All right, so then Q square, the Q tests, the I squared statistic both suggested low heterogeneity among the studies included in the meta-analysis. I squared is up to 0%. P value is about 0.55. Q is about 3.05. So, which is what you all said, there's no heterogeneity, right? Which you could find from the studies. What can you draw? Conclusions can be drawn about the effect of T on influenza. Reduces the risk of influenza infection, about 28-29% reduction in influenza risk. About a 9% is okay. That information is not there. Then there's also about this publication bias. What do you see? The 5 studies is too low, right, to assess publication bias or anything. But even in the 5 studies, what you would expect, you would get symmetry. There is no studies are missing on the other side, right? So how they discuss about publication bias? Did you find any discussion on publication bias? 5 studies, totally about 2,000 participants, reduces the risk of infection, influenza infection, compared with control activities, which could be anything, as you were saying. And they have the sentence on first study, first meta-analysis to consider, probably the first meta-analysis on. Now, the conclusion, do you agree with it? Also, would agree. Then I read further, they say, it's like how you all mentioned, small number of studies. Mean study heterogeneity is yes, because most studies are conducted in Japan, right? There's touched on a very important thing on generalizability. Limited generalizability findings. And then they also said, see, we don't know about some of the things that you mentioned in terms of subgroups, like prospective and randomized control trials. There's a small number of studies. If the number of studies increase, then you would look at sensitivity analysis to see how things actually. with that, if you have any questions on the paper or anything, because they have the fixed fee model, IC, BIC values, it's like less than random. What could be? Why they use both? See, sometimes what people do is kind of a mental shortcut, right? Suppose you don't want to think really about heterogeneity. You don't want to think, is there a significant heterogeneity? Can I talk about this? If you don't want to do that, an easy way is that you do both. You can do both. It's just a matter of toggling complexity. Then, yeah, because there, for example, I have a way, 10 years, that's the weather kid. Yeah, actually, so COVID, there are many toggling, toggling, systematic reviews that are toggling on many and other parameters also, like does it increase your immunity, stuff like that. So you can actually look at after COVID, there's like considerable number of analysis on. But I would say, see, yes, first of all, if you ask me, if I'm the person who's doing the meta-analysis, I would do regardless of what it fixed effects are. If you ask me what's the reason, why are you saying fixed effects? I say first, there has to be substantial reasons for you to assume or expect effect of an intervention to. You're not saying that if you're doing a random effects model, you're assuming that each study is estimating its true effect. Right? That's what we are assuming. That's the assumption behind the model. And for that assumption, we are calculating one extra parameter called tau square. Right? We are calculating the tau square. Means we are making one additional assumption. We are also estimating one additional parameter. There are a parameter for it, you have to use advanced methods like the restricted maximum likelihood estimation. Right? And then the things that come along with it. So in fact, if you are doing random effects model, there are many studies that show what's the best method to estimate tau square. The restricted maximum likelihood estimate is one method. There are few other methods as well used to get a better estimate of tau square. So there itself there is a lot of certainty in terms of good estimate for tau square. So for me, that sounds like simple math, but and also when you're trying to interpret, you're saying that it's an average of the. So because I would actually choose a fixed particular, still I can evaluate and look at heterogeneity, easy to interpret, easy, requires less assumptions, unless you have a very strong reason want to calculate. Does that you understand?
Uh,
Yeah, the we all got a WhatsApp document. What I want y'all to do, open the RevMan. 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 And you start a new review. New review. You can get this next. And we're going to do a intervention review. Right? So enter any name you want. Private point for repeat. Private point for Y back. So we have two options. What should I choose here? Protocol or review? Full review. Why not protocol? Yeah, so the protocol stops with the method section. And the only references you can enter is additional references. That is to support your background and all. Doesn't allow you to go beyond that. So the review starts after your method section is done, in which you have explained how you're going to search for studies, where you're going to search, how you select, all of that. So we'll start with the full review and we finish. So before you do anything else, I want you to understand that this help file is important, right? Because there is this help question mark. You press on that, it tells you how to use RevMan, how to enter data, how to extract references. So please read this. We'll tell you how to become familiar with everything in RevMan. If you have any doubt about using RevMan, please go to that help file. Okay. So if you want how to create subgroups, we'll show you, but you'll forget. So go and read that section. And you have to type in that creating subgroups. It will take you to that section and tell you what to do. Okay. The second helpful thing here is you can click on handbook and it will take you to the Cochrane site where you can get the handbook. So while y'all were saying, it's very important to read and all that stuff and read reviews and stuff. A lot of things you don't understand, just check the handbook. It will tell you what. So the useful things are you want to plan a review, up all kinds of stuff, starting the review. These are the core methods that ideally you should read before you. So you can use the same thing for a non-Cochrane review, right? And if you want to learn more about meta-analysis, there is a chapter here. You want to learn about network meta-analysis, there is a chapter here. All of that, risk of bias, everything there's a chapter. So please read that. Okay. If you want to learn about economic evidence, somebody had some questions about that. There's a chapter on that. You want to learn how to combine qualitative synthesis, there's a chapter on that. Okay, so that's a very useful resource you should not ignore. And if you're interested in diagnostic test accuracy review, there is a handbook for that. And the same RevMan can be used for diagnostic test accuracy as well as this. Okay. Then if you want to learn more about the statistical algorithms that are used in RevMan for all the statistical analysis they do, there is a PDF file which will give you everything you need to know about that. So 2 by 2 table, continuous data, ONE variance, all those formulae are there. If you want to appear smart in front of your students, you will copy these formulae and present it. But they might ask you questions, then that will be a problem. Then the other useful thing is there are online learning modules. For that, you'll probably have to become a member. You have to contribute in some way or the other. And so using RevMan to create any document you want to publish elsewhere, non-Cochrane, use cite RevMan like this. You're allowed to use it, but cite it. Computer program RevMan. Okay, so we did our analysis using RevMan 5.4.1, probably a 4.5, 4.2. And that version, you can put that as a reference. Okay. Now, what we have to do is any study you finished your protocol and you searched, that is when you're going to, and once you got your search results, is when you start finishing your review, right? So, what's the first step there? You screen and you selected your studies. Right. So, you'll have three files, included studies, excluded studies, right? So, for those, anything in RevMan, what do you have to do next? You have to import the references, right? So we showed you on the day how to import references, but today I just want to do an analysis. If I want to do an analysis, I need studies, right? So I'm going to bother only about included studies right now. And like Mohan taught you yesterday, we want to add some studies. So I want you to do is open that Word document. It's got, I sent you a Word document, and that's got risk of bias figure. You got the risk of bias figure? It's got a list of study IDs, right? Enter those study IDs separately. That study, and just the ID. We're not interested in the full reference for the moment. So the first one is Alvarez, 2008. So you go to included studies and you have two options to add a study. One is right click and add study. Second is you look here on the top left, there's an icon. It is add study. You can use either option. Yesterday you did right click and add study. You can do the same thing, you'll get the same box, pop-up box. Okay. So what we're going to do right now is add Alvarez 2006. And ideally, if you're handwriting, entering all the references, you click next. And it will ask you, where are you getting this from? Is it a published data only? That you only have a paper? Or do you have published and unpublished data, which means you've got additional information from the authors? Then you can choose that option. So this today, or if you've got a completely unpublished paper, some report, conference presentation, which is not reported in any citable format, then you've got the manuscript, you can write unpublished data. Okay? Or you can say, it's published data only, you have unpublished data, but you're not using it for this. Don't worry about too much, but gives you the options of adding these sources. Where did you get the data from? So I am going to say publish data. Then if you say next, you keep going next, you have options. One next is the year. The year automatically, in the ID, you put Alvarez 2006. The program picks up that and puts 2006 there. Okay. Put another next. You have the option of adding your identifiers, which is your ISRTCN, that is a study registry, that is the International Clinical Trials Registry, or you can add a DOI, Digital Object Identifier, that DOI, you can add that number, or you can add the clinical trials gov, the registration. Or if it's our registry, CTRI, you can add the other and you can write CTRI number. Okay, that way that gets tagged onto that reference. Then next, we'll ask you what do you want to do. You can just leave for today, we are just going to leave it like this, nothing. But otherwise, you can add a reference to the new study, or you can add another study to this. Sometimes you'll have 5, 6 papers all pertaining to the same study. That's one way of adding the reference. You're manually adding it, you can do it. Use this. Anyway, for right now, I'm going to say finish. Sorry, I'm going to say next. Okay. I'm choosing nothing and finishing. So now I've got Alvarez, one study, doesn't have a reference. I'm going to add the other study. So will you please keep adding? Don't wait for me. You've got the list of studies, just add. I want that entire list. And I want you to do this exercise today because we're going to do a meta-analysis. And for tomorrow's practical session on grade, we will need this meta-analysis plot. Because tomorrow we will take this RevMan pulse plot and shove it into another software on Grade Pro and do the grading on that. If you do not do this today, at least in the evening or sometime before tomorrow, please complete the forest plot. Any question, any doubts? Out of chatter, any doubts? On the risk of bias document, you will have a lot of study IDs, right? So please enter those study IDs. Is that clear? You can do that also, no problem. Right? You should have 15 references. 15 references. And you're finished. Right? You're finished. Now, what do you need next? Come. Data. No, 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 no. Ask me what is the next step? Enter the references, you read the paper, then you're going straight for the data. For a film study state, first go to the Alvarez and you go to the table section on the things called tables. Wherever you see the little icon there, right? On math, it will come as an arrow. There it comes as a little toggle. So that means there's something under that. Okay. On that, you see another characteristic study, there's something under that. Then you characteristic of intuitive study, something under that. On that, all your references have come there. It's already in reference section, but the moment you enter a reference, it's also copied into this section. And if you look at Alvarez 2006, there's something under that. Right? Click on this, you have to next enter this section. Right? So normally workshops bring you the paper and say, do that. But I'm feeling in a good mood, so I'll not do that. Then what you got to do is you got to do a risk of bias assessment. Okay, doing all this meta-analysis will all finally what? That we can automatically do a panel to say, you want to change your practice on this. So this meta-analysis and the risk of bias and this study sections plus information make our grade assessment. Yes. So proceed systematically. You will need to know where it was study done. What is it comparing? That kind of information. Guys, how are you going to do a meta-analysis? You don't know. There are so many comparisons. When you start entering your mind, no, I've got 15 studies comparing, 10 studies comparing 14 days with no primer. Right? That's how you classify comparison. That you can only do systematic. So now what you got to do is the Word document and make sure get this, be able to generate this figure. So how will you do that? Go to the risk of bias for each study, right? You know, Alvarez is seen all through. That means low risk. Okay. So what we have to do here, go to Alvarez, random, you choose low risk. Right? And you choose low risk for everything. At the paper, Alvarez told you how he the random sequence, and you decide this is the method I can conceive. Not a method I cannot conceive. What do I mean by that? I read the paper and I'm saying he has used the method which can then, that list of random numbers can be conceived. What do I mean by that? Yeah, so I got a method that gives me a randomization sequence which I can conceal from the person who is selecting participants. So what are those methods? Yesterday in risk of bias you did, no? Adequate, inadequate, no one showed you. What are the adequate methods of allocation concealment? What are the inadequate methods of allocation concealment? Which are the inadequate methods? Date of birth, day of the week, alternate number, all that kind of stuff. So you can't conceal it. Right? So he would have said computer generated code or something, and we would normally write what method he used, computer generated, and then we make the choice, low risk of bias. So the point is this: whenever you have your default option is unclear risk, right? You may think it's unclear and leave it like that, but it will not. Computer will not know that you've done anything. So that's a default option. So if it's unclear, I have to write something. Then only the computer will realize, oh, he's actually filled in something here. Otherwise, he'll think you left it blank. But if you change from unclear to low, then you have made a choice. So even if you don't have, computer will pick up that you attended to this. Okay, so in this first study, we are lucky because we just have to click low for everything. Okay. Then the next study is Carmona-Francesca. We go down till we get that risk of bias table. All start off as default unclear. Also, we can click low for everything. But you must give a reason. So people will know why you said low, because they may read the study and think, why are you saying low for this? One of the other things you need to know when you're doing a risk of bias table on RevMan here is that you see the risk of bias and there is a tiered wheel. What does that mean? Properties. That's an icon for the properties of the table. So you click on that so you can know what it is. So there are things that are activated and you can activate or inactivate any of these things. Okay. So here, what I have got here is blinding, allocation, concealment. I can actually create a separate one more item. I can say, for example, uh, blinding of outcome assessment. I want to know what is the blinding for the outcome assessment from this study for subjective outcomes and what is the blinding outcome assessment for objective outcomes. Right, because it matters. So I can create one. I can just say add new item. And I can create one tab, blinding of outcome assessors for objective. And I can edit this one. I can edit it. I can change this one here, detection bias. So what you then have is you can expand the list of outcomes so that we saw in ROB2, they're asking you additional things. No, outcome by outcome by outcome you have to assess. The one outcome is pain and the other outcome is mortality. You're assessing it through different methods. So mortality doesn't matter if it will not blind you. Whereas pain, it matters. Right. So when you have done the one assessment for the study and you already divided it, right? When you want to assess the overall risk of bias for that outcome, you know what it is here. You understand what I'm trying to say? Make it easier for yourself to know subjective outcomes and objective outcomes have to be assessed separately for risk of bias. Any doubts about that? Okay. But we are not going to add another outcome, so now I'm deleting it. No. If you edit the table, it will edit for the whole thing. Wherever you find a properties tab, you're editing for wherever that property is. By way of my review, I have added. This is the new review, not added yet. The Word file was generated. Hang on. The Word file was generated from a review of the actual review that I've done, which if I open my RevMan, I have a window option. So I have now two reviews here. If I want to see my actual review, this is my actual review. Okay, and if I look at the risk of bias here, here I've got random sequence generation, selection bias, blinding, performance bias and detection bias for objective outcomes. So I've combined performance and detection and same for objective outcomes. And what are these objective outcomes? Parasitemia and serious adverse events, right? And I've got another thing saying blinding, performance and detection bias for subjective outcomes and other adverse events. So I'm evaluating the risk of bias for these separately. Okay. And then when I create the figure, it will come like that. But because this is a new review we've added, I have not done all that. It can take time, but this is how we can do it. But anyway, as far as we are concerned, for today's exercise, we just want to fill up those tables. So don't please wait for me. Go ahead and enter. Put your Word document and enter. So Ganguly was high on risk of bias for finding performance bias and other bias. Ganguly's methodology. Sorry? That she treated as one. Choose one. What you have to do for Ganguly is you're saying that blinding for performance and detection bias are subjective outcomes. So whichever is there is a red, you choose red for that. Okay. If you have anything you're leaving unclear risk, you have to write something. I'm just writing not reported. So, so somebody was asking me yesterday, if the data is not clear, is there any point writing to the authors for them? Will they reply? So Gopte is an example of this because Gopte was a person who works in NKM Hospital, Mumbai. I didn't know her. The first version of the review, the paper only said re-randomized, nothing else with it. Right. So in the first version of the review, we were unclear. Right. Second, first, when I going to revise the review, while I was thinking about revising the review, I'd gone for a conference. And after the dinner, we were going back to our respective hotels. And there was this lady sitting next to me, and we started talking, and I realized she's Nitya Gopte. So I said, hey, I've been wanting to talk to you. Did you do this trial? She said, yes. Can you tell me about it? And so I didn't ask her. I said, how did you do all randomization? And she told me we had a computer generated randomization, sent it to the pharmacist. Pharmacist did all this. And she told me the lab technician went to the house of the patient and took the blood smear. Right. So I learned a lot. I said, okay, I'm going to send you an email saying this is what we discussed. Can you go back to me and confirm this is what happened in your paper? Why? That I printed out. And that's personal communication. I have it with me in case anybody asks, where is your evidence for this? So if you're getting a letter back from someone, you keep it as, and you can enter it as a reference saying personal communication, dated so and so. Okay, that will come under one of the references for that study. So let's finish. All green except for incomplete. Once you've done, finish it, the next step, save. Never keep it, know where it is. There is a tab here. Third one is save one. I've already saved, so it's grayed out. But if I do anything more, comes back again. Okay, so the third thing on top is a floppy disk icon. Shows how old it is. The other option is you go to file and you can save or save as some other place. So have you got this much done? Oh, go ahead. So you realize you've only done this much in a systematic way. There's lots more to do. Now, what is this footnotes for? In case you use an abbreviation, you can add that for that table. Similarly, for your included studies, excluded studies, there will be that footnote can be for anything to do with this entire. If you want to make the left pane more easy to navigate, you can collapse the studies. So it becomes easier to navigate. Has anyone finished? Then kindly make a figure out of this risk bias. How do you do that? How do you make a figure out of this risk bias, like the one you have in your document? So keep looking to the left, see anything which says figures. Under data and analysis, on the left, there's figures. You click on the figure and you can right click on it. It says add figure, or when you highlight figure, the same plus button will come and ask you add figure. You choose what figure do you want. So bias graph. Click risk of bias graph. Tells you what you will get. You get a plot of the distribution of the review author's judgments across studies for each of the risk of the bias item. Is that what you have? No. So anyway, let's try what this risk of bias graph is. It asks you caption. If you want to change the caption, you can change it. Risk of bias graph, whatever you want, you can change. It's editable, right? And then you click finish. And this is what you get. So this is not what you. Oh, what this? Okay. No, no, no. Oh, happy they are. Now I can do it myself. Not all you. Okay, now what we want is the same document that you have. How do you get that? Add figure and choose the next risk of bias. Only two risk of bias, no? Choose the other one. And that will give you what you will get. So if by chance you have not written anything is unclear, you won't get yellow, you will get white. It doesn't matter. As far as you're concerned, that is unclear. Okay. So any doubts about risk of bias? There is a chapter on risk of bias in the handbook. Please read that also. Okay. Now the next thing we want to do, we have assessed risk of bias presumably we read the papers and we know all the next section is actually, in the thing is a figure, we have to do a qualitative assessment and we have to do a Prisma flow diagram, study flow diagram, Prisma template. That's the next thing which has to happen. Right? You practice on your own how to do that. So we are now going to do analysis. Since yesterday you already started analysis, what should we do here? Everything you right click and it says add comparison. So remember the way you do meta-analysis, you are comparing two interventions, right? And in this review, when you read all your studies, you know what are interventions, your comparisons you have. So every comparison is separate, right? So for today, your data you've been given in your data sheet is analysis one. CQ is chloroquine, PQ is primequine, 5 days versus chloroquine alone. Okay, so what should we do now in this? What should we do? I will write plus versus like the 5 days. You are right. I guess balloons. Okay. That is the main comparison. First comparison. Next, what do I want to do? I can decide. Okay, I'll enter the names of all my outcomes first. I can do that. Now I'm outcome. So I will say add an outcome. So I add one outcome, or I can add multiple comparisons. For 5, 6 comparisons, I can enter all the comparisons. Go back one by one by one, add the outcomes. I can do that. Right now, we'll add an outcome. It asks you what kind of outcome is by call. You have to enter the number of participants with events, total number of participants, parameters, and control. That data we have. Then we want to know what name of the outcome. Parasitemia and all that, but you just write map. Right. So, what should I write? Experimental. What should I write? What your data have you cured? Must be 5 days as your experiment plus control. Question is saying standard of care in this don't want to give chloroquine at all. Then chloroquine alone is what you're doing. So you just write plus P 5 X. What should we choose? The options are statistical method, so and first variant. So the default option for these kind of comparisons, and I as a clinical risk ratio, odds ratio also, and it asks you to expect a fixed effect or a random effect. But quite what we discussed this morning. How do you decide? You have to ask yourself, expect it to be good, right? So if you want to start off saying, I'm going to get studied from different parts of the world and the other, I might get some. I'm going to use that. The other way of looking at it, you say, had a very combination. Say the chloroquine and thing on drug trials. not going to get that much. You have to justify in your mind why you do. Doesn't matter because why some kind of heterogeneity in the model, whether you reflect as right now, it's fixed. It's fixed. Doesn't give you any other option. As far as dichotomous data, you take which method you want to use, what measure you're taking, and what model. Yes, Then it says next. Now you have a choice: totals and subtotals, totals only, or no totals. No totals means only you've got one graph. Now don't want the diamond. Just want the line. Suppose you only have one trial. Hey, there's no point putting a full one trial. No totals. Hey, start off with we are not going to do a subgroup now because usually we look at subgroup in terms of exploring heterogeneity. That's one reason you'll do a subgroup. Or you might want to say, want to stratify my results that initially opposite. Now I have to give a graph. What a tell you must write what it is. Experimental. What should I write here? Right. Right. And I can order it according to the study ID. That means like the alphabetic according to the first authors. Or I can order by the year of study. There's any or I can order it by the weight of study with more events and the narrow confidence come. Or I can do it by effect size, various things. Study ID, right? Always change it around. What do you want to do? Nothing. Pick the new outcome, add a subgroup for the new outcome, add study data, or add another outcome under the same comparison. Nothing. Why not add study data? Because you know the outcome, and we can proceed with adding studies, no? So add study data. Even if you say nothing, you right click and the same thing will come up. Okay, but when you're right clicking, you should not right click on data analysis, you should right click on the comparison. If I go to data analysis and right click, you can say add a comparison. Right, that's a tree. Data analysis, you are adding comparisons. Under each comparison, you are adding outcomes now or studies. Right. So if I go to the comparison and add outcome, I can add one more outcome. So I have to add an outcome. Yeah, we haven't added outcome. Right. So add outcome. Have you finished the outcome? What? I added the outcome. That will see. So whenever you do this and you stop, you know something under that. Right. So see, I've got the outcome. Now I can add a subgroup or I can add study data. I want to add study data. The studies I need the Gopte, Roland 2 and the others 2000. Control and putting control and choose all three. It opens up like okay. Got that? Right. Enter the data. So to enter the data, I can just take like this, copy all the guys enter. I can actually copy and paste. After all the problems, transferring data, you got to keep double check. Actually, you have two authors double check. Double check. Okay, now how do I get the forest plot? You see this little thing on the side here, this toggle switch. I that it like this, or I have a fluorescence going to find this forest plot right. Right? That's the forest plot. So for meta-analysis, I want to know the thing is what? What is the effect? Effect is 0. Ratio 0.96 means 4% reduction in lapses 5 days. Right? That's what the effect is. But confidence says it could be better or 18% reduction, or it could be worse, 12% increase. So it statistics, the p-value at the bottom shows 0.61. Not statistical. Right. So basically it tells you that giving 5 days of primary quiz as good as sorry, 2.6, 2.61. Second should be like 0.5. Not 6. Now the next thing we have to think about when you're looking at thing is heterogeneous. They're heterogeneity. So heard about the chi-square test. Chi-square test. Every time when you see chance, chi-square test. Chi-square test has a chi-square value. Yes. So why is the freedom 2 here? 1 minus number of trials. So the rule of thumb is the chi-square value. Don't worry about that because you also have a p-value to accompany. P-value tells you 0.05. But 95% sure, chance. Percent a chance. The I-square tells you that 66% of the difference in the results of the trials from analysis exceeds more than what can be accounted for by like, there is a little bit of heterogeneity. Right? And what is more important is the confidence intervals overlap. The first one's one limit is 1.08, right? And the figure so much, sometimes you cannot make out. That's what I'm telling you. what you then need to do, get your slider. The bottom toggle, you can adjust it. So I can see now, like this, you can't make out really the overlap. But when you do this, you see there is overlap. All three confidence are overlap. Right. So as we were discussing in the morning, what is really important for us about, is it an important thing for us to learn? We got two studies. One study saying it works 5 days better. The other one says, but the third one says mostly don't listen. So if you can find some reason to group it, that's one way to go. The other option, want to leave it like that, you can leave it. Or what you do? Change to random effect. Right. Toggle here, fixed effects, random effect. When you use random effects, sometimes much more clear that you don't know. What has changed? The weights here 36, 8, 10, 15. And if I say fixed, third study is not given any weight effect. Why? Confidence interval is very wide. Right? As the fewest participants, event rate in the control group is not very high. Therefore, automatically variance will be wide. And your confidence interval. So once you've done this, you have the option of adding it as a figure, or you can save as a figure in the plot. Right. So if you say save as a figure, save this, say add as a figure. Now your review's got more figures. Analysis 1.1, come as a figure. The other option is you can copy this analysis, paste it in a Word document. That also you. So you can use RevMan as a template, write the rest of the review in Word. Okay, that's one. I am not going. Questions on this? So we're talking about what kind of data? Dichotomous. Right? So the next example I can give you. I'm not going to give you, ask you to do it as homework. And, and particularly, want you can do this one also. All the studies are already there. You don't have to add a study ID. You have to create comparison to the data and see what it is. But you look at this, whatever written here is SB 2004, 2008, and Roland were given more than 6 months free. Right? SB 2004 and 8 were cluster random. Some context what this data is about. Okay, so suppose I want in this I want to write something about this study of day. Right? I want to say this in Bombay. Right? I highlight that. I've got a graph up, find that one is there, gives you an idea of something about the trial. Right. So if I can say, put that trial, right? Leslie was a randomized, was a cluster randomized. Any footnote you want to to understand the graph better, what you have to do is find that study, highlight it, write your note there. I want to do this. I can write something there. Here order 1, 2, 3. Now save this file. Your homework for the other next analysis, categorical. All of them are from save the review because we can use it tomorrow. The other thing you can also do now, I want to assess something else. I can just press got this icon, you can press this. And now I can see what is the risk of bias forest plot itself. It will come in handy tomorrow when you grade research. Next one I want to do how to do a so what you have to do for a mean and standard deviation kind of thing is you're running a little bit short of time. Asking you to enter if you practice that. I want to add another outcome. We're going to call a continuous outcome. So I give the continuous outcome a name. I can say index, whatever name. I leave everything as it is. I click next. Now it's asking whether I've chosen mean difference. It says inverse variance is the method it's going to combine. I have an option of choosing mean difference or standardized. By measuring every study is measured this parameter side index. Okay, I will choose difference. Now, next, everything else is the same. Next, so that so really when you're using a thing like this, you can write what was it add correspondingly, give you additional information. What is the and what was it? What came from how much to how much? Pain scale. Say unit there is pain scale, whatever scale you take. Next, I want to add study data for the new outcome. I continue. I can arbitrarily choose. What's the difference now? Standard now. Got you. Okay. So continuous data like this. Then what do you think? Looking at the data, getting they're using HD here, right? But the mean is minus 0.4. Change. What they've done here, they're looking at the change score, baseline score on endpoint score on baseline. Difference between point and baseline, right? That is what we come. How much change occurred in the control oxygen group on that rating? How much change occurred from the beginning to the end? Right? So each study, this one in the first group, the score was reduced by 19.44 units. That is, right? They're comparing the change score, 19.44 and 17.7. That difference is what you see. Right? So you have to enter that kind of stuff. Change score means reduced, lower than the the original. Get this on the paper. The paper will report it. What you're adding. No, 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 no. You have to enter a negative sign. But it doesn't know what it is. And the table will, I'll have to label it as change score. I'm writing the text. I can edit the outcomes right here. This same meaning. But if it says it is less than 5%, chances are when you active drugs, score is going to be less. The high score is at it will be minus. Comparing the two, how much once you enter that, then you get a mean price. Copy everything. But what you have to do for that is you have to enter in your passport or the same review, but you will have to add these references. Or on those references you add as the same if you want. Here, open another review and add these. Right. Then you can do that. And the other thing you need standardize difference. Because there's one use PST diagonal rating scale, one use another rating scale, one use another. Right. That one use endpoint scores. Compare at the end. Take the base. We're looking at change score. Right. So if you want to combine all of this, combine it, you standardize mean. All you'll be doing is difference to assembly. Back, evolution, the analysis tab. Those will be all added the same. Try that. Okay. Now, last thing I want to ask Am is tell us something about when, when you're doing educational study. What kind of data you want? But I can show you example of generic inverse variant. I have data for that I review. This is an analysis of 7 days of primaquine versus 14 days. Right. What is this? What I have here, the perfect for prime 14 days versus no primates. I have subgroups about the outcomes. What kind of data is this? Till now you are entering either dichotomous data or mean. What? Log rank, log risk. So what you RevMan has got a beautiful thing. This is a calculator. A RevMan calculator. Want log risk ratio. You got paper data for in each of the group. That's how many people got in that group had the event, how many in the other group had the event or the non-event, and if you calculate the totals, it will calculate everything. Right? And it will fill up everything here. Just have to choose which ones you want. Show, log, odds ratio, calculation, risk difference. You enter the numbers here. So I'll just take 1 and 103, 1 and 101. That's all I have to do. I only do that. Everything. Log risk, confidence for the log risk ratio. Right. When I cancel this, now if I want, when I'm doing it, I've got Gangu, nothing is entered. I've only got the idea of course study. But I like that study and I press this, then I enter those numbers. I do this. Right. So suppose just for now, going allow me to have data there. I can do just remember those numbers back to me. One, one, that is the now what? See, now the update data table has become less on that, the log risk ratio, everything. Okay, so the very when do you use quick inverse variance? I told you that Leslie was a cluster randomized. Right, and we discussed the other day what a cluster randomized trial is. You're going in this families are being treated with the same 5-day regimen or longer day regimen. Right. Now the problem in cluster randomized trials is even if I'm giving the same treatment to 5 different or 10 different families here, and I'm comparing the other thing, the results within the family are likely to be similar. Why? Contamination. Because of that, for example, whether people take the medicine or not in that family is determined by the person who makes decisions in the family. So if it's a chaotic household, nobody will take medicine. And another household, they're very, very organized, everybody will take medicine. So the results are clustered together. So if you combine cluster randomized trials along with individual parallel trials, the cluster randomized trials will get more weight because their confidence intervals will be more narrow. Right. So you have to do a unit of analysis correction for it. So if you anticipate in your study, your protocol, that you might get cluster randomized trials, right? Then the problem is you have to look at the handbook. It tells you how to adjust for clustering. If I were to go back to the data, look at this. Leslie, I've got a footnote. Risk ratios adjusted for clustering. The inter-cluster correlation is 0.32 and the design effect is 1.34. Now, if you read that section of the handbook on clustering, you will understand how to adjust for clustering. Right. So that's what you have to consider. So if you want to combine cluster randomized and non-cluster randomized trials, you have to use generic variance. Only thing is, all the other parallel group studies can also be converted into log risk ratio. And I told you how you can do that. Just have to open this box, highlight the study, enter the numbers. It will calculate everything for you and shove it back into the box. The other thing is, you might find some studies where they have only reported adjusted log risk ratio because they did some calculation to adjust for something else. Then you cannot use the original raw data. You have to use the adjusted log data. For that particular study, You click on this, you just enter the log risk ratio. You don't know the numbers and all. You enter the log risk ratio and the confidence interval for the log risk ratio. You can update that table. Or you have some, you enter the adjusted risk ratio. You enter this, you get an adjusted risk ratio and confidence interval. That's what you get. You will enter this and that and that. It will calculate the log risk ratio. And you can add it to the table. You're all looking really wiped out. Okay, what did you understand this first bit? The first bit about I've got Ganguly. This bit, I got paper. He tells me that in this arm, one person had an event out of 100 people. And in this arm, one person had an event out of 102 people, out of 103 people. Right? Now, this is one bit of paper I can analyze using just the routine risk ratio. I don't need log risk ratio or anything of that sort. I can do my typical categorical risk ratios. But if I've got many studies and some of the studies are using a different design, like for example, cluster randomized trials and parallel group randomized trials, combining them, I have to adjust. I cannot use a regular random. I can combine them using what do you call the generic inverse, this particular thing. Okay, so if all the studies are only like this, and I've got data for all like this, I just enter the wrong numbers. Even the cluster randomized trial, I have to adjust for clustering statistically, and I'll get a different set of numbers in this arm. That I have to. So if you have a cluster randomized trial, take it to a statistician and tell them, please give me adjust for clustering and give me the numbers. Those numbers you enter here. Okay, and it will combine everything. The other thing is, sometimes you've got 5 studies, all are cohort studies. You've got 2 groups, they're all cohort studies. They've done adjustments, and all the studies are reporting it as log odds ratio, log risk ratio, or something. Right? With not log odds, or adjusted odds ratio, adjusted risk ratio. You have papers like that? Anyone looks at observational studies, cohort studies? Usually how do they report the results? They'll give you adjusted risk ratios, right? You take the adjusted risk ratio, enter it here. Nothing else you need to do. Just enter the adjusted risk ratio at the maximum. If you want, they might ask you what is the sample in each group. That's what they'll ask you. That and this and that, it will fill the rest. And highlighted that study itself, that update study table will become visible. You click on that, it will go into that. So you've got 5 studies with adjusted risk ratio, the adjusted ratios. You add it here or you add it. It will give it to you. Okay, that's the way to do a meta-analysis of these risk ratios or odds ratios from observations. And suppose you do find one observational study, they have not done any adjustments. They're just giving you the raw differences. You bung that in there. So that's how you can do a meta-analysis of that. Any other doubts? Now, what kind of data do you get for ONE? I've never used it.
With observed values and the experiment and the control. Sometimes it just a report log hazard rate and the control.
So if you have the log hazard ratio and the confidence interval, if they give you log hazard ratio, you add it there. You can convert the hazard ratio into a risk ratio, and you enter that risk ratio there. That's all you can do. This is probably better than using that method. But it depends on if you have those. They give you the risk or just the risk. Do you have any doubts, sir?
Like in studies which are reporting the overall survival. Now, in that, actually, some they say mean survival, some they say median survival. Somebody gives confidence interval, somebody does not. Outcome will be a pooled overall survival, which intervention or control are. In that, actually, if you can show like from the effect size outcome selection, which one to select, and if those information
First, first, then you can enter it in RevMan.
no, in RevMan, see, the difficulty that sometimes with this information, odds ratio, it is not a time to event event. It is at a point. If you can show one illustration where time to event data, how to enter in the RevMan, where survival is the outcome or disease-free survival is the outcome.
That's what, na? Various illustrations I made in the morning. No, suppose in a paper.
Software.
No, you can't enter data on survival as such. There is no option of entering survival information. You will have to. That's why I said in RevMan, generic inverse method is the only method. So you go to this and
This is the way to combine.
exactly.
What you have to do is get it into any one of these forms.
Yeah.
Right? And the number come. It will give you this. If they have given you a log risk ratio and confidence,
Enter it
that.
there.
Like hazard ratio.
Hazard ratio.
Risk ratio, yeah.
That in a paper I sent you. That we have no more doubts. You can see
Everything.
have this. But how many people at the event? How many died? Like this, that group. Just enter that. You mentioned country. Just yes.
And they will say the median.
Now, what you need calculator is then what is the IQR? And there should be IQR.
In median survival time, they don't give IQR. Just give median survival time. Hazard ratio they give. They give hazard ratio. That feed in there.
It's an adjusted hazard ratio. That there.
If they give you hazard ratio and confidence interval, for example, if they give you hazard ratio and confidence interval, then convert that into natural log and enter it there in that column. The rest of the things will automatically.
And do is one, enter the CID, open this. Whatever you get, automatically.
Other question.
I suggest that you practice at home, your own guys.
But most now tomorrow again.
I think about converting all these one to the other is the most simple thing that you need to learn to do. Setting up a comparison of your outcomes, dichotomous or is once you do first. Get all the complicated. The other thing I want you to do for tomorrow is go to Pay Pro. Just Google RA
Microphone.
Just type in greatpro.org and you'll come to this thing, right? You can create your own account. For tomorrow, you please do today itself. Just go to greatpro.org and sign up. It's free. Just sign up and come. So tomorrow when we are doing the grade, if you've got at least that one prime thing review, don't worry, even if you don't do it, I'll give it to you. I'll show you a way in which you can get that RevMan file. Okay. The other thing I can even suggest you do a homework, save time tomorrow. You go to the Cochrane library. That's the same thing that we did in the first day. I'll get this study, Gauri Galapati. I'm opening this. Now watch what I do. Watch what I do. Okay, I've got the HTML version of this, right? I go to results. Oh, sorry, figures and tables. I go to figures and tables. Oh, analysis. Sorry, just after analysis, can you see this thing which says download data? Analysis, download data. It tells you have to agree to the same terms and conditions that you're not going to do nasty things with it. And if you've got RevMan in your computer, you download it this will be the file. Right. This is actually the RevMan file. Right. This review comes. You get the whole review. Only thing is, it'll be blank. The only thing will be there will be the plain language summary. Everything else is blank. But you'll find those study references are there. Physical bias assessment is not there. Analysis is all there. Every single analysis, meta-analysis is there. So, for example, we were looking at time equivalent 5 days, 14, first 5 versus 14. So, even if you don't do your homework, we will help you. If you got the data, you can zip this into RevMan, Grade Pro tomorrow. Okay, thank you.
Thank you, sir. So, with this, we come to the end of today's session. So, I request Professor Amit Agarwal to felicitate our esteemed guests today, Dr. Prasanna and Professor Geeta Menon.